going to continue the OS Dev here today. I'm thinking about making a physical memory manager as I have in my, test OS here. It'll work similarly to how you're going to see it right now. I'm going to have a physical memory manager to actually allocate sort of blocks of memory that we have available to us. So I'm using a BIOS interrupt that I'll get to in a second to get the physical memory map of the system on boot. Get that from the BIOS, and then I'm using that to basically allocate the available space and then reserve any space for like the kernel or BIOS data area and stuff like that. So after doing that, we have our total memory on the system. I am in 32-bit mode, and I said to give it, the full 32-bit address space. So 4 gigs of space is this in hex. And then we have the total amount of, I'm using 4 kilobyte blocks to be easier for paging and things later. So the total number of 4 kilobyte memory blocks out of this space is this number. The used or reserved blocks are this number, and the amount of blocks we have available for user programs and kernel use and everything is this number. So 32598 multiplied by 4 kilobytes is effectively how much space I'm going to be working with, at least until we eventually move into 64-bit mode or physical address extension for RAM or something else. 32598, 4 kilobytes, 4096 bytes, so, this many bytes, which would be about this many megabytes. So really it's not that much, but it is a lot, so oh well. And if we need to, free up some other stuff or reserve it later, that's fine as well. But I will get to it. What I wanted to end up with is, I sort of want to just only manage memory within the kernel. So that starts with managing RAM, and then we'll get into virtual memory sometime later on after I learn how that works, and paging and all that. But if I load a file, like the file table, we want to allocate memory for that file that we're loading. We want to allocate memory at an address, as long as we have enough space to allocate for the stuff that we're going to load. And then I'm loading the file to that address that we allocate, and then, for this purpose, I'm just reading a text file, so we read it to screen. But we could be loading a program like the editor or the calculator, and after we're done with it and we return to the kernel from that loaded file, or processing that loaded file for a program, I'm going to free the space that it took up. So I made a command that just prints out this info in case you want to see where you're at later on. We could use that to detect memory leaks, I guess, if we don't free memory. But if we, load something, we'll say the editor, that takes a few blocks. Do a space. We'll just load it and then exit back out. The editor took up 3 blocks instead of 1 block. But right now the first free space is at A000, so everything's been loaded to there. That's okay. That'll be, how it is for a while. I don't have a multitasking, multiprocess kernel or anything. So it's a single tasking OS, and it'll continue to be that way until I develop that stuff later. But the way we're going to start is by using a BIOS interrupt to get the physical memory map, so I will go into that. Okay, so this is the OS Dev Wiki page for detecting memory x86. I'll probably have a link to this in the description. I'm using BIOS interrupt int15, 15 in hex, and then EAX E820 in hex. So this detects memory, gets a physical memory map of the system. This was defined within the ACPI standards. This is the latest ACPI spec 6.4 as of, I think, January this year. And just to show where I got the ACPI specs, I went to uefi.org. If I just go to the main page, although I think I'll provide a link to this stuff. I think it's under developers specifications library. We have the latest spec like right up here, this PDF or HTML link. I went to HTML. That's where I found this page. But the OS Dev Wiki page said, I think, at least since, PC's built since 2002. I wanted to see what actually first happened, because I don't know, I was curious. So I went and found their previous specs, which is on the main uefi.org specifications library. ACPI prior specs gets to this page. I went to the first one here, which is from December 22nd, 1996. Text is a little small. And that is this page here, so these all point to the same thing. I just kind of wanted to show that, this did exist before 2002. At least the standard existed as of December 1996, revision 1 of the ACPI, which is Advanced Configuration and Power Interface spec. Okay, but this is the same thing as the other pages. It didn't really change much. But this is, actually reading it from the standard. You can use int1588 or E801 to get, ranges between low and high memory and everything. But it's easy to just use E820 because it gives you everything, low through high memory, everything that's defined on the system. So it'll give you everything below 1 megabyte of memory and everything above pretty much. It'll give you different sections inside of a memory map that you lay out. You tell it where the location is with ESDI. You give it the sort of number, the region of memory that you're looking for, that you want info on. You put that in EBX, you start at 0, and after you read in one of the regions of memory, it'll increment or put EBX to the next number. So you keep passing that until EBX becomes 0 again, and then that kind of resets the map. You can stop there. You need SMAP and EDX, or since it's Little Endian, this will probably be backwards. It'll be like PAMS. And that tells the BIOS that you want this system map. ECX is how big each sort of memory region you're trying to get the info for. Each entry for this is a certain size. It's 20 or like 24 bytes. So at minimum, you should set ECX to 20. I set it to 24 because that's what the OS Dev Wiki, I think, recommended. But you'll get stuff like the base address and length of memory and the type of memory, pretty much. So that's what I'm using. Yeah, on return, EAX will have SMAP if it's correct. Otherwise, carry may be set to indicate an error. ESDI is the buffer you wanted to point to. So the descriptor that goes into ESDI each time you call this, you'll have 4 bytes of a base address, 4 bytes of the high bits of the base address, because they're 32 bits, low 32 and high 32. So these are 64-bit addresses effectively. And length low and length high, how long of memory is. So this will say like your base address low and high could add up to 0 for the first region of memory. So your memory will start at 0, physically your RAM. And then the length is how much memory you have for that region. So 0 to like 1 megabyte, say. Although there's usually memory hole there, so it's probably only up to like 640K. So it'll give you that length in bytes in this length, split between low and high, 32 bits each. So 64 bits for the base, 64 bits for the length, I guess 4 bytes for the type as well. So the type of memory that it returns will tell you if it's usable, which is 1, it's available just for use by the OS. If it's 2, it's reserved by the system. You shouldn't really be using that. If the number equals 3, it's ACPI reclaim. So if you read the ACPI tables, then you can use this. I don't know how to read the tables yet, so I won't be doing that. ACPI NVS memory. I don't know what NVS is. I should probably learn that as well. Otherwise, it's undefined. So if it's like 5 or above or whatever, I'm probably just going to set those to reserve so we don't mess with that, even though these might be available. They're undefined. At least as of the first revision. Although in the latest revision, does it even say, I don't know, extended attribute, address range types? Well, this gives more, doesn't it? So there are different types here in the latest revision as of this year. But I'm really only going to be concerned in looking with like the first 4 or even 3, whatever's returned by QEMU and or box, I think is only 3 or 4. We won't really be worrying about these. If it's 5 or above, I'm just going to set it to reserved. And that's fine. So for an implementation of how to actually do this, I'm sort of taking the OS Dev Wiki approach because they already did the work. If I go down to the bottom, getting an E820 memory map, this has code in assembly to do that. So I'll be typing this out, so don't worry too much about having to squint and read it. But basically you're setting a location where you want the memory map to go, and you're setting up the initial values. So the first 4 bytes, they are storing the number of entries. So they can use, something like the base pointer, which is, you can use that to store the number of entries here. And then store each entry starting at 8004 because the first 4 bytes are the number of entries. EBX was the continuation. That starts at 0 to get the first region of memory. This is the hex for SMAP they're putting into EDX. E820 again is the BIOS interrupt. They're forcing a valid ACPI entry. So because the extended attributes comes after the type, which they didn't, in the first spec, they didn't define that. But there are, I know I keep switching around, sorry about that. There are extended attributes for ACPI that could potentially be in here, although they aren't really used. They just have, must be set to 1 is bit 0. So that's why they're setting this to 1, because it says, hey, it must be set to 1. We want a valid entry. And at max right now, it could be 24 bytes, even though usually it's just 20. So they're setting it for saying, yeah, this region of memory in the memory map is going to be 24 byte entry. And 15, if the carry is set, you get an error. Otherwise, we can reset EDX to smap, see if EAX is smap, which is success from calling the interrupt. And if EAX is not equal to that, it's an error. If EBX is 0 at this point, then there weren't any entries to read. We had some other error, or there's only one entry. Otherwise, we have a valid entry. We're just resetting and getting the next one. If the length is 0 in the entry, then there's probably no useful info in there. ECX is set with the actual length. So if that's 0, there's not really a good valid entry. We're skipping that. Otherwise, we can check if it's normal or if it has the ACPI info in the last 4 bytes. It would be 24 bytes in that case. If it's not, then we don't have that. I guess this is not extended. I thought it said no text, but that didn't make sense. Otherwise, they're getting the length of the memory, and they're just putting it in the memory map and stuff. Okay. Storing the entry because it would have incremented. This is at the end, I suppose. Yeah. So this would be the next call. Should be here. So if it's not extended, we do this. Otherwise, we skip it. But either way, we're resetting EBX, and we're going back. If EBX is not 0, since EBX is the... I was on here first, right? Since EBX is the continuation value, after you return from calling the interrupt, if this is not 0, you have more stuff to read in for the memory map, so you keep calling it until EBX is 0. So that's why they're testing that down here. If it is 0, then we've ended, and we get the number of entries. If it's not 0, we go and get the next entry. That's what that's doing. Or you can do it in C, I guess. But this is in real mode, so they have this. So I guess it would put the size prefixes in front of the code if we did this. So I'll probably just be doing it in the bootloader in real mode. That's fine. But this is, a typical map that you can get. So the first low memory, 640K or 639, starting at base 0, it would return length. It would return the type as the first type, which is freely available. Same values return using int12. So you can also use interrupt 12, which will get you basically the length of, or the available amount of low memory up to 640K. But everything beyond the first 640K memory, you would need to use this or other BIOS interrupts to find info for. So everything that says address range memory here is available memory. So in this configuration, they had 640K plus 7 megabytes plus 120 megs. So about 128 megs of available memory. But anyway, I'll be putting that into the bootloader. So we will get on to that. Okay, so I'm in my regular OS here. I'm going to be putting this BIOS interrupt call into the bootloader specifically. The second stage bootloader, I'm going to be putting it up here at the top before we do all the Visa BIOS extension stuff. I'll be putting it up here. One thing I did was just reset ES. So I'm using an ES:DI buffer for this memory map, and we also use that for the VBE stuff. So I'm just going to reset ES here so that I don't have to do it down here in the VBE. Otherwise, I'd have to do it twice, and I'm just, 2 lines of code instead of 4 lines of code. Very small refactor, but there you go. I guess I can show int12 because I didn't really explain that. Int12h gets you basically the area of low memory available up to 640K. So really, you can just do int12, and is it AX or EAX? AX is the number of kilobytes of low memory available. So it starts at address 0. So this number will be the number of kilobytes starting from address 0 that are available. I don't know, maybe it's cool if you want to look at that. What this does effectively is get the data in the BIOS data area at area 413 in hex. Number of kilobytes of low memory in BIOS data area. I'm not going to be using this, but I don't know. It's a little fun digression, I guess. But this is just for debugging, but I can show what these values are by doing this. If we go in and make the thing and run it, it will halt because I just told it to halt. I think we do info registers, right? But we can't see the stuff at the top. That's okay. We print what's in EAX. We have 27F. 27F is the number of kilobytes of low memory. So that's 639 kilobytes of low memory. So, which is what the ACPI spec had in its example anyway, 639K. It all comes together. But also, if we check in EBX, which is loading the area in 413, the BIOS data area, it's the same number. So all the interrupt does is basically retrieve that number from the BIOS data area. You can use either one if you want. I don't know why you'd want to, you know, how much low memory you have. Maybe you're working on an extremely constrained system or something, but that's one easy way to get that. But the E820 hex BIOS interrupt call has that info in the first region that it returns anyway, so I'm not going to be using that. That's just sort of an alternative specifically for just low memory. This will be BIOS int15h EAX E820. So this does require a CPU that at least has, I guess, size prefix code or whatever, because you'll need to be able to call or use EAX and EDX, you know, from real mode. So it needs to be able to reference 32-bit registers. So, you know, I guess that's one limitation for really old CPUs. They won't be able to have access to this. So, but everything since at least 1996 probably should be able to use this. So ESDI points to buffer of 24 byte entries. BP will equal number of total entries. So I'm going to set this up similarly to how the OS Dev Wiki page example, how that was. So I'm going to set up a area of memory to put this in. I'll just call it mmap entries. I put this at 85. Okay. This is just an arbitrary location that'll probably change later, but it's out of the way of other stuff. Just 8500 hex, just some memory location. Store number of memory map entries here. That way we can retrieve from this location in the kernel. We can read from it. I tried to make my labels a little more descriptive than other sites. So I'm moving 8504 into DI. Since the number of entries is at 8500, I'm saying that could be up to, you know, a 32-bit value. That can be up to 4 bytes for the number of entries. So I'm storing the actual memory map entries here after the number of entries. So 4 bytes after the 4-byte number here. So EBX is going to contain the continuation value for this. So I'm setting it to 0 to start off. So I'm doing that. BP I'm going to use like the OS Dev Wiki had. BP will have the number of entries. Okay, EDX needs to have SMAP, but since we're in Little Endian, I'm going to write it backwards. So I'll put PAMS, because that just, I don't know, on some level that makes me chuckle a little bit. And then EAX, again, needs to equal E820 in hex. You do it like that, put the 0 there. So the first memory map entry and then each additional one, I'm going to set a 1. So I'm going to move a 1 into the sort of ACPI extended attributes area just to say, hey, this is going to be a valid ACPI entry, whether or not we have any info at that point. You know, like the OS Dev Wiki had, I'm going to force a valid ACPI 3.x entry. Okay, and I'm expecting each entry to be up to 24 bytes in length. And then I'm going to actually call the interrupt here. I'll have a little error label down here, just in case. Function not supported or errored. I forget which exactly, but if the carry was set after calling the int15h for this, it means the function errored, you know, or it's not supported, but I'll just do that. So I'll have error down here. But if it was successful on return, EAX should equal SMAP. So again, Little Endian, so I'm going to compare it to PAMS. If it doesn't, we add an error. Okay, we'll test EBX first off. So this is just a way of doing, you know, compare EBX to 0. You can also do like an OR EBX with itself or a test. They would both set the 0 flag in the flags register. So yeah, they would both set the 0 flag. This is just shorter. This is less bytes, because if you compare to a constant value, this 0 is going to be expanded to the length of EBX, which is 32 bits. Instead of needing 4 bytes for this constant value, we can use like test, and this will only be like 2 bytes or 3 bytes maybe. So save a couple bytes there. Does EBX equal 0? If so, only 1 entry or no entries. Sad face. Okay, otherwise we're good. I'm gonna go to start this whole thing. EBX not equals 0, have a valid entry. Okay. Jump CX 0. So after we read each entry, if CX is 0, that means the entry doesn't have any data associated pretty much, or maybe it's junk. The entry is 0 bytes in length instead of up to 24. I'm gonna jump to, I guess, skip entry, right? Called it, yeah. We want to skip this entry. 0 bytes in length, skip. Otherwise ECX is greater than 0. So into ECX, I'm moving the length value. So that's ESDI plus 8, which is low 32 bits of the length. And then we can OR it with the high 32 bits. And also by doing the OR with that, OR will set the 0 flag, so we can test if it equals 0. So then if it's a 0, we can go to skip entry as well. Basically this says if the entry length was bigger than 24, but the length of memory that was returned within the memory map entry. So if it says it starts at 0 and the length is 639K, right, that's valid. But if it says it starts at 1000 and the length is 0, we're not really interested in a memory map entry that says, hey, we don't have any memory here. So we're just skipping that entry. The length of the memory returned was 0 in this case. And we don't really care about that, so we'll just skip that one as well. So I had another label down here for skip entry, of course. Also, I didn't write it, but put it above here. Because I didn't get to it yet, but I'll have one for next entry as well. And there will be a final one down here called done. I'll get to these in a second. But if we didn't skip any entry, then we had a valid entry, so called good entry, which is fine. Just putting a bunch of labels, you know. If we had a valid entry and there was actually length of memory returned, we want to use it. It's good. We want to increment number of entries that we're going to store within this mmap entries memory area up here. And then to get to the next area inside of our memory map address, since each entry can be up to 24 bytes. We're going to store the first one here. The int15 call will store to this area because it uses ESDI. So after we've stored the first call or whatever call we're on, whatever entry is stored here, we want to go to the next memory area to store the next entry. Since each one can be 24 bytes long, I'm going to go to the next 24 bytes offset from wherever we started from. So I'm going to add 2di 24. So that way the next call to int15 will store to, this plus 24 for the next entry, and then we'll add 24 again to store the next one, so on and so forth. Okay, if we skip the entry, if it was not good, or if we got a good entry and we're just going down here, I'm going to test EBX to see if we still have numbers to go. So if EBX not equals 0, still have entries to read. EBX is the continuation value. If it is 0, then we're done. So I'm going to go to done. Otherwise, I'm going to jump to get the next entry. Okay, if we have an error, we want to test an error, I'm just going to set the carry flag. That's all that's going to do. Done will clear the carry flag. And done will also move into memmap entries BP. Store number of memory map entries when done. Okay. But I do have this next entry thing just laying out here. So what are we doing here? We're doing basically this call and setup here again. So I'm going to reset EDX to PAMs. Could be BAM like Emerald Lagasse, but we're not doing that. We're doing PAMs like Pam Beasley. So according to some articles like OS Dev Wiki, some BIOS may clobber EDX. Reset it here. So reset it to SMAP. Reset ECX to 24 from whatever value it was after we got the length. Reset ECX for the next call. And reset EAX. I don't remember if EAX is clobbered. I guess it might be though. And then we'll call it again with int15. And then we can determine if we return 0 bytes, then we'll skip. Otherwise we get the length. If it's 0 bytes, we'll skip it. If not, we got a good entry. It has been stored at ESDI. So then we'll add for the next memory to store it at. If we're done reading entries, we end. Otherwise, we get the next entry, do that again, so on and so forth. So at the end, we'll have a bunch of entries stored starting at 8504. The number of total entries stored here will be in 8500. That is the whole purpose of this, and that will get the memory map. Get that all on one screen, but that's, the only code you really need to do that. So that is good. We can then read from this address and then check what it is in the kernel. So I will do that next. Okay, the one thing I forgot to mention was if we want the VBE code and everything to work after this, we need to change this line right here. This was move AH for F. This is what it was. AL could be set to whatever from up here. Maybe AL is just 20 or whatever from this EAX change. But that will not work because we need AL to be 00 to actually get the VBE info block and move on here. So I just changed this to move AX for F00 to explicitly set AL, and then, that makes the VBE info block, that BIOS call works, and this other code still works the same as before. But if you don't have that set, you'll get like an F when you go to a boot. But with that, for F00 now into AX, everything works again. So just wanted to show that. But okay, I'll get to actually putting these stuff in the kernel now. Okay, let's continue here. I'm going to have a little separate function or section to print the memory map. I'm going to make it separately from the kernel main section here, so I'm going to, declare it globally here. I'm going to call it print physical, either memory map or memory info. I'm just going to put info. Print physical memory info. It won't take in anything. So print information from the physical memory map, smap, if you want to call it that. I'm going to have a little global sort of structure to hold each entry in that memory map that we just did with the BIOS function. The reason I'm doing a separate function is because I'm going to have another shell command like print directory, print reg for the registers. I'm going to have like a print memory map function that'll print this out. I'm just going to have this be a separate function here so I don't duplicate code everywhere, right? A struct here for the memory map entry, each one that we read and print to the screen. So I'm going to call it like smap entry probably. And it's going to be kind of laid out how it was said in the ACPI spec. The first 64 bits are going to be the base, or the base address. The next 64 bits are going to be the length. And the next 64 bits, if we have them, are going to be split into the type and the ACPI. So it'll be 32 bits here. The type, whether 1, 2, 3, 4, whatever, 1 is available, 2 is reserved, so on and so forth. The type of memory, and then the last 32 bits, which we don't really have, but we put it here anyway because the spec said to put it there. As the ACPI attributes, I'll just put ACPI. That's fine. We're not really going to be using that anyway. We do want this to be like just 1 byte aligned pretty much. I don't want the compiler to say, okay, this is on some arbitrary 4 or 8 byte alignment or whatever. I want to make sure it's exactly 64, 128, 192, right? So I want to make sure it's exactly on 192 bytes for each one of these. So I'm going to do attribute, I think it's double underscore, yeah, and then double parentheses, attribute packed, and that'll make sure this is exactly what we laid out here in memory. It won't be optimized or on any weird alignment boundaries or anything. And then I'm going to call this smap entry t, just so we have something there. And then to be able to use that in the program, I'm going to have a global one here. I'm going to call it smap entry, or I can make it in whichever function we're doing, which I might do that as well. That might be easier. So I'll go ahead and just put this at the bottom for now. But that's our, our memory map entry structure. Okay, and I am going to make this at the bottom down here. It's going to be a function. I'm going to put this inside of that function. Okay. I'm also going to have a 32-bit thing for the number of entries we have here, so I'm going to call it num entries. That's fine. This will be the number of smap entries that we got returned from the bootloader. Okay, so what this is going to equal is going to be the 32 bytes at, so I'm going to dereference a 4-byte pointer here, the 32 bytes at the address that we stored the number of entries in the bootloader. So down here, since we said the number of entries is at 8500 in hex, I'm getting the 32 bits at 8500 in hex, and then I'm dereferencing that 32 bits to get, you know, the 4 bytes for the actual number of entries stored at that address. So that's what I'm doing here. The smap entry, each entry was going to be stored at 8504, so I'm going to point that to 8504. So this will be smap entry t pointer to 8504. This will be memory map entries start point and the number of entries there. Okay, so what we want to do is just read through, you know, this many bytes each time and just kind of parse out the entries in each one of these structs and print it to the screen. That's all I'm going to do. So I'll have a for loop here for I equals 0, I less than the number of entries. I'm going to print the string. I will have to change these to be global as well because I'm referencing them here, but I'm going to print the string basically according to each of these sections here. So the first thing returned is going to be the first region of memory that was mapped, that, you know, the BIOS is returning to us. So for each region of memory, I'm going to print out that number, which is basically just the entry number here, or I, in this loop. That. Then we'll print out, I guess, hex right now. Kernel cursor X, kernel cursor Y. I did this a little differently than my test thing, so I'm going to have a couple other things to go over later, but that's okay. The region's going to be I, so the first one, it'll be region 0, then 1, 2, 3, 4, you know, whatever. And after the region, we'll print out the base address. I think I want it to be a little different. I'll have region, number, and then a colon, and then base. And then the colons will be region, colon, 0, base, colon, you know, whatever the base is. This will be smap entry, be an arrow because it's a pointer, base address. After the base, we'll have the length. So this will just point to length. So this is very straightforward. After the length, we'll have the type. These probably don't need colons there. Base length, the type. This will be type. I have a little, these don't need to be this far over either. I have a switch case here. On smap entry type. We'll have 1, 2, 3, 4, or others. Case 5 is just going to be like the default here. Okay, case 1. I'm going to print out. Still need kernel cursor X and Y. So type 1 is sort of freely available RAM and memory, so I'm going to print out available. Get this off the screen, available. Let's do that. Okay, type 2 is just going to be reserved, general reserve memory that we shouldn't be messing with. I'll just do this actually. Let's type in. Type 3 is going to be, what was it, ACPI reclaim? Yeah, ACPI reclaim. Type 4 is going to be ACPI NVS memory. I don't know what NVS means. I should probably look that up. And then the default is going to be reserved. So default. I'm going to have break statements, aren't I? So yeah. Let's do that. The default's just going to be reserved as well. So we're not doing fancy ACPI things or anything. And then after that, that's basically the whole the whole memory map entry for that, so I'm just going to do a new line, put the next one on the next line, so do that. No, that'll go down here. I'll just copy one of these lines. Zero A, 0D, just for a new line. And then to get to the next entry, since we have a pointer to the entry, and each from pointer arithmetic, it'll go that many number of bytes to the next entry. If we just increment it, I'm just going to, increment it, and I'll get to the next entry in memory, which should be 24 bytes away from the first one. And then after we print all of them out, then we should be okay and good to go. That's probably all I'm going to do for this. Okay, so let's see if that works first, and then I'll print out the amount of memory. Because I might want to do, I'm probably going to change how print hex works first, so I just want to see what this looks like before I do this other stuff. We'll have print total amount of memory, print out, later I'm going to do the memory manager proper. So I'll print out memory manager block info. That'll be later. Okay. We'll see what this does first off. Does not like doing those because the cursor is not global. So I'm going to make those global. Wherever that was, these two. Still does not like those unidentified. Kernel Y. Yeah, that's probably why. We're going to do that. Oh, and these, yeah. Cursor. It would help if I could type. I can't. There we go. Is that good now? Nope, no closing brace. 528. Oh, extraneous, yeah. There we go. Now it's 16. Actually, that's not going to print to the screen, is it? Because I didn't actually call it. Let's do that after here. Print memory map info. Print physical memory info. Is that what I called it? Yeah. I'll probably put a couple new lines here as well. Maybe I should have a routine for printing new lines. That'd be easier. We'll do 2. Okay, now how big is it? 16. So I'll have to change it in the file table. That'll be 16, which is 22. Which means the other ones need to change. This will be 2O, 2C. That'll be 15, that'll be 16. Now this should be good to go, hopefully. See what happens. And we print out the memory map. Alright, so region 0, base 0, length FC. It's longer than this, we just have a 16-bit limit in print hex right now. Type 1 is available, 2 is reserved, served. Available, reserved, reserved. Okay, so we have a couple regions that are available. The first, it'll be the first 640K, but this doesn't print right, it's truncated, so we need to print out more than that. So I'm going to change how print hex works to be able to work with the variable sizes instead of just one set 16-bit. So I'm going to get to that. Okay, so let's change the print hex file here. If I can get out of that. Alright, we'll change this a little bit to take in a larger value to start off with, but I'm going to change this to only print out the value that we get. And what I mean is only value large enough to what we pass in. So if I pass in like an 8-bit number, something 15 or less, or 255 or less rather, I only want to print out up to that. I'm not really going to pad it out with zeros or anything. Maybe I could do that later. So I'm going to make this up to 32 bits because that's our largest address space, at least for right now, that we're going to print out. I also need to change, well, I don't need to, but this has been a typo forever, so I'll change that. This also takes in 3 inputs. This will be hex number. number to print. Okay, not that that matters, just wanted to fix that. Okay, so it's going to be 32 bits. I'm not going to have this string anymore. I will keep the ASCII numbers. I'm going to make a different type of string here, an array of characters. I'm going to call it hex string. So I'm going to print out a string. Right now the maximum that a string I'm saying is going to be is 80 characters. So the maximum this is going to be is 80, although that's like way higher than we need it to be. But that's okay. I'll just make it 80 right now. We can change it later. I'm going to have I, J, and temp because I'm going to be swapping values later that you'll see. I'm also going to have a flag if I want to pad out with an initial 0 or not. I'm not going to be printing out negative hex numbers, or else I'd have like a negative flag as well, but I'm not doing signed values here because I don't want to limit to half of the available numbers that we can print out, because I'm going to be using this for memory addresses and things. Okay, if we pass in a 0, I just want to print in a 0, print out a 0. So if we passed in a 0, I'm going to copy into the hex string that we set up just a 0. So that's simple enough. Just copy those two characters there into hex string. I'm going to use I later as the sort of position in the string that we printed out to so far. And you'll see why in a bit. I know I'm not explaining much, but that's just how I had it typed out. I'm going top down. But if we passed in 0, print a 0. If we didn't pass in a 0, I'm going to see if it's only 1 digit long. So if we're less than 16, so if we're only printing out 0 to F pretty much, then what I'm going to do is pad it out to zeros later. So I'm going to set pad equals 1. So I'm using a pad flag to be like if we're padding out with a leading 0 or not. That's all that's doing, just so everything is at least 2 digits printed out on the screen, because I like it better if stuff looks like, 0, 0 to FF. I don't like just, I don't know, 0 to F 1 digit because I'm weird. I just think it looks not as nice. Okay, so instead of just doing 4 bits each time, shifting left 4 or right 4 places to get each byte, each nibble, I'm gonna basically keep reducing the hex number by 1 hex digit until we're done printing it out. So while this is above 0, convert it to the ASCII string, that's fine. We get the nibble, we AND it. Instead of doing hex string 5 minus I, we're putting it into I. For each digit, I'm going to put it into the string here, and then shift right by 4 and increase I. So this will say, the first digit goes into the 0th position in the hex string, the next one goes into the next position, so on and so forth. Okay, if it's only 1 digit though, if we only passed in hex A, right, then we're going to pad it out. So if I'm padding it out, I'm setting the next digit equal to a 0, just the character 0. This will end up putting a leading 0 on the front, so it's at least 2 digits. But okay. And I'm going to add the prefix to the start when we print the screen. I could also add the suffix h, but at least in my test I did 0x, so I'm going to keep it this way for now. So I'm going to add the 0x to the front of the hex string. So with I++, we'll just add in the x and the 0. I'm printing it backwards for a special reason. You'll see soon. 0 and x. I'm going to read the string backwards. Since we stored the number into the string, it's been stored sort of backwards. So we have to read the string back to front to print it out. That's also why I made an I variable to keep the position of however far inside of the string we are. I'm going to null terminate the string first. I'm going to reverse the string by swapping ends until they meet in the middle. I'm going to skip, if I can type, so move past the null byte at the end. Okay, so I'll move right before the null byte that we terminated with. What I could do is just do I+1, and then I won't have to do that. That would be better. But I'm going to swap each end of the string until they meet in the middle. So I'm going to do that in a loop here. J, I'm going to start at the front of the string. I is currently pointing to the end of the string that we want to print, although it's backwards. So until we reach I, I'm going to sort of squeeze the ends in the middle from the front and the back. I'm going to swap those and then move, next one to the middle, swap those, move next to the middle, swap them. And then when they meet, we're done swapping the ends of the string. We can print it out. So that's what I'm doing. That's what that's doing there. I'm just going to use a separate variable to swap them. So temp is going to be hex string, we'll say I, or J rather, it doesn't matter, but hex string J, J will be I, and then I will be temp. The standard swap that everyone does, using an extra variable there. Yeah, temp is J, J is I is temp. And then we just keep doing that until they meet, where J is greater than or equal to I. And then this will swap the string in place. It will be, instead of, reverse, it'll be basically front to back, not back to front, and we can print it out to the screen. And we'll see what it looks like now. So printing may be off for like print directory and reg. They might look a little different. Does not like that. Incompatible, yes. What doesn't it like? Hex string. Oh, I didn't type that out right, did I? Need to replace that. And that, because that's the new variable name. That might make a couple of those errors go away, and it made a lot more though. Assigning to UN8T pointer from int. It should be okay. What did I not type out right? Probably everything. Yeah, sorry. I was too focused on it being a string that I was thinking of a character string and not an array, which is already a pointer. That was a pointer to a pointer. I don't want that. I just want the regular array here of characters. Yeah, if you have this asterisk, get rid of it. Don't do that. Don't make the same mistake I do, please. You do that and everything's good, except for implicit declarations, which is all right. That is in the calculator. Okay. That is okay. I can include string.h in here, and that error will go away in the calculator. It'll also make the calculator probably larger, and it did. So 16, 1E, and 0D. So this is 0D now instead of C. That is okay. So this will be D. Now we should be good to go. All right, let's print everything out. So this looks a little different, and it's wrong. This is almost what I wanted to happen, but 0, that's right, but the X is over here, not where it should be. That's a little off, but you can see these numbers are at least larger, right? And these are smaller. This looks like, yeah, that's a little off. 0, 1's right, but not this other stuff. Okay. Oh, I put it at I, it needs to be I. I guess I will do I minus minus here, never mind. Getting ahead of myself and it doesn't work. Okay. I will null terminate the string here. And then I'll move before the null termination and then swap the ends and then print it out. That might make it a little better. Hopefully. Yeah, that's what I wanted to do. Okay, I add the null hypothesis. I had the null terminator in the wrong place there. So we can see now we have region 0, the base starts at 0, the length is 9fc, and the type is 1, which is available. So 9fc00, 654 approximately. So how many kilobytes is that, sir? That's about 639K, which is what we expected. That's the amount of low memory available before the memory hole, before 1 meg, and that memory hole between 639 and 1 meg has the extended BIOS data area and other things. But after that, we have reserved area from 9fc to F0000, length 400 in hex. But then and that's reserved as well from F quad 0 to sort of 100,000. This is the 1 megabyte mark, so hexadecimal is cool like that, which is nice. 10000, 100,000. Approximately 1 million bytes, 1,000,048. This is the 1 megabyte mark. So at 1 megabyte, until about 7FE0000, we have available memory, so that's cool. Let's do 7FE, or wait, no, let's do 7EE. 1234 minus 100,000. 7DE, which I should have done that in my head. That's this much amount of space. And bytes, that's this many kilobytes. Approximately 125 megs. So it's a little over because the Windows calculator rounds values down and everything, at least in programmer mode. But that's approximately 120, 130 megs that we have to work with here. Total available space, that's a good amount. That'll fit us for a while. Then after that, we have more reserved areas. I'm sure if we had a 64-bit system, then we'd have other ones beyond this that are, free. But right now, this is all we have. All we have is 130 megs out of 4 gigs, right? That's not much, but that's okay. That's whatever this QEMU system has. But what's cool is that we got new print hex. What's not cool is that this needs to be changed so that the stuff lines up better. But print reg should be okay. That looks all right. So let me change the directory command right quick. That will be in print file table, right? Yeah. So I need 2 more between like the sector and the file size. So the starting sector will make 6, and the file size, this will be 11. And that should fix that up for the directory. That was the last 2. Yeah, so just 2 more here before the start sector and size, 2 more blanks until we change it later, because these will be bigger. But right now, okay, we're printing out the regions of memory and everything. That's all good. So the next thing we could do is maybe print out the total amount of memory here, which, well, we don't really need to, but I could do that anyway. It should say 4 gigs. So let me go ahead and just print out the memory right quick so I can confirm that we have all the 4 gigs available. Yeah, I did that all the way at the bottom. Print physical memory info, print total amount of memory, okay. So I'll print a string here. I don't know why I keep trying to type it out instead of copying. Takes less time. Say total memory in bytes. It'll be in bytes. And we'll have print hex. Whatever the final entry in the SMAP was, will give the final, base address and length. Those will add up until the end of memory, and that will be our total amount of memory. So I can add the previous base address and length together from the SMAP entry to get the total amount of bytes that we have, if that makes sense. So we can add in whatever we ended on is what SMAP is going to be pointing to right now. Although this is ++, so I might have to subtract it first. All right, get last SMAP entry. Since we did a ++ every time, I have to do that first. So we'll print that base address plus the length, and it'll be -1 because that'll be the 32-bit limit. It'll be 1 over if we don't do that. It'll be 8 Fs, which is the 32 gig limit, plus 1. And since that number can't fit into a 32-bit number, it'll roll over, and I don't want to print 0. I guess I could show if it actually does that by checking first. And print out another new line after that as well. Although I don't think I need to. Okay, yeah, see it prints out 0, it goes 1 extra. If we add this base address plus this length, that should be all Fs, but that also rolls over to 0 because it's an unsigned 32-bit number. Okay. So we need to do -1 for that, and that should give 8 Fs. Okay, there we go. FFFF, FFFF. There we go. That's the 32-bit limit, 4 gigabytes. So that's nice. I don't need the final one here. I would like to actually put that here though. That'll look a little bit better. If there's a little space between this. There we go. That's what I wanted. Okay, so this prints out the regions of memory from the physical memory map, the BIOS interrupt, prints out the total amount of memory in bytes. So now that we have this info, we can use that to our advantage. We can make a physical memory manager and allocator to allocate some memory blocks and bytes out of this whole address space that we have. I can sort of initialize areas of memory that we can use. I can deinitialize areas that we don't want to overwrite, like the kernel area or the memory map that we put it wherever we put our memory map into, our physical memory map, not this S map. The BIOS data area, the interrupt table that we'll eventually have. I don't want to overwrite that stuff, so that's going to be sort of deinitialized or reserved. But yeah, I'll go ahead and probably start on the physical memory manager next. Alright, let's make the memory manager here. I'm going to have it as a separate header file like all these other things I have here. So I'm going to make another directory. In the include directory, I'll just call it memory. I'll make a file in there called physical memory manager.h. So there should be no confusion about what it is. We'll be making this and we'll be including it in the kernel. If not other programs, probably only in the kernel. I only want the kernel to be the sort of single source of truth for managing memory around the OS, so probably we'll only have to include it in the kernel. But physical memory manager.h, this will have functions or provide functions to allocate free or handle blocks of physical memory. I guess we'll just call it, I'll call it that. Okay, like with the other headers, I'll do the pragma once. I'm going to have only like a couple constants, I think only two that I'm going to have up here, but I'll just make them defines for simplicity. We'll have the size of a block that we're going to be working with. This physical memory manager is going to work with memory in terms of blocks, so just some abstract chunk or area of memory that we're allocating or freeing. Or our block is going to be 4K. So 4096 bytes, 4 kilobytes, or kilobytes, however you say it. That'll be the block size. And then another one, I forget if I used it. I might have only used it once or twice, but I'll have it here anyway, just to remind myself. So be blocks per byte is going to be 8. So I'm going to be using a bitmap allocator. I'm not going to be using a stack, which other physical memory managers have used, at least from cursory research that I did. A stack may be easier in some cases, maybe better performing, but I'm doing a bitmap because conceptually it was easier for me to understand. 1 byte is 8 bits. Each of those bits is going to handle 1 block of memory. So 4096 bytes times 8 is going to be the amount that 1 byte will manage. I'm on a 32-bit OS right now, so we're going to have 32 bits at a time that I'm going to work with to make things more performant. So we'll have a variable that's, 4 bytes, 32 bits, that'll handle 32 blocks at a time, but I'm just having this here that we might use in a couple places. Blocks per byte is going to be 8. So we're going to be using a bitmap. Each byte will hold 8 bits or blocks. I'll have a couple global variables though. I don't think these necessarily need to be static. I made them static because that's what a tutorial I found did. And that kind of ensures that wherever this header file is included, these variables are only going to be within that header file. I think that's what static means, at least in the global namespace. If it's in a local, like a function block here, and we use, some static variable or whatever. If we had static within this, then this variable would keep its value between function calls, right? So if we called this function a few times, this variable would not be reinitialized. If we did like this, it would, the first time it's called, it'd be 0. Second or third and fourth, this would keep its previous value. It would not be reinitialized to 0. But I think the global namespace here, this will be a 32-bit one. It just means that this variable is only going to be accessible. It's only going to be like visible within, they call it like a translation unit, I think. So whatever file this header file is included. So the kernel, basically, I'm going to be making like a variable for the memory map. This will only be accessible within the kernel. Basically the point I'm trying to make. I forget how the exact wording goes with that, but I'm making it static. unit 32, of course, needs to be int. I will initialize it to 0 to start off with, though, but this will keep its value after the first initialization, so that's okay. So I'm going to have a pointer to our memory map. If we work with the memory map, it'll be in terms of, 32 bits, so 4 bytes at a time. That'll be 32 blocks, so a good chunk of memory at a time to make things a little more performant. Second variable here, I'm just going to have a couple for the maximum number of blocks that we can have. Just to be, if we want to check it within the kernel or other places, I'll have it be a global variable here. And I also want to check how many blocks are currently being used. So I'm going to have the current maximum number of blocks overall and the number of blocks that are used. So that will determine what we can free or otherwise, use. Used blocks we don't want to overwrite. I'm going to have a couple functions here to see if a block in the memory map is used. So I'm going to have one to set a block or a bit in the memory map. So this will mark it as used. Mark block as used. Just do void. I can call it set block or set memory block or something. I'll call it set block. It'll take in a number to set, bit or block. I don't know. I called it bit, so I'll keep it bit. We'll also have one to sort of unset a block. Call it unset block. This will unset a block, which will mark it as free, so it can be used again. If it's used, we can't use it unless we free it first, so that's what this is going to be for. And I'll have another one which will test a block. Is set use. We'll call it test block. This is just going to return if it's a 1 or a 0, if we set it or not, if it's available to be used or not. That's what this will be for. But what we're going to do is take in the bit, we're going to divide it by 32, since each chunk that we're working with the memory map is going to be 32 bits at a time. If we pass in like bit 33, we want to divide it by that to get the sort of 4-byte area that we want to offset into to set this bit, this block. We're going to be working with 32 bits at a time, so we want to get the start of whatever 32-bit area we're going to be setting. So that's what this is doing. Offset into the memory map by however many amount of 32 bits we want to go. Into that 4-byte area, I want to set on some bit. So to do that, I'm going to OR it with a 1. Shifted left. Basically, whatever bit we passed in modulo 32, right? So I'm getting divided by 32 to get the 32-bit chunk that we can offset into. And then when I get the remainder of division by 32, that'll get the actual bit within that 32-bit chunk that we want to set on here. So hopefully that makes sense. That's why I kind of spelled it out here, because I'm going to forget later. I'm going to be like, why did I do this? What does it do? So yeah, we're getting the start of this chunk of memory. We're setting that bit within that chunk is all we're doing here by dividing and then moving left by number of bits from the remainder. 32-bit OS, I'm working with 32 bits at a time. So unset block is going to be pretty similar, but slightly different. Instead of ORing to set the bit, what I'm going to do is and do not. I think that is the only difference here, and that will set a 0 in that place instead of a 1 in that place. Okay. So if we send it like a 33, we want to do set bit 33, 33 divided by 32, integer-wise would be a 1. So it'd get memory map offset 1, which would be 32 bits after the first 32, which would be 0, and then it would OR 1 bit after that, because 33, or modulo 32, should be 1 remainder. If we wanted to unset that block, it would get those, but then it would, do an inverse here, do a not. If this was our memory map and we sent to set like a 3, or well, let's change it. Let's make, for whatever reason, we'll say it looks like this. If we passed like set block a 3, and we use the first chunk here, because 3 divided by 32 would be 0, we want to OR it with 1, shift left by 3. It would set in 0, 1, 2, 3. So it would set this one to a 1, right? If we wanted to unset that block and we passed a 3 into here, this is 32 bits, but let's just pretend this is 8 bits right now so that this example makes sense. We'd have the 1 shifted left to here, but if we did the inverse with this, what we would instead would be anding with, these would be 1s actually. We'd be anding with this, except this would probably be a 1, but if we and with this value, then this bit would be set to a 0, and the other ones would still be 0 because they were 0 to begin with. If these were all 1s, and we set to unset bit 3, then effectively we would be anding this with this value, which would give us, you know, this value. Does that, hopefully that makes sense. That's not a good example, but I'm not the best at explaining. To test a block, instead of anding or oring the thing, all we can do is just return that bit. We'll just return this anded with the 1. So we'll return that bit. We get the bit that's offset within this 32-bit chunk, and we just return it, whether it's a 1 or a 0. This will return that just by anding this. That will return a singular 1 or 0. So yeah, say we had this, and we wanted to get the status of bit 3. You know, we'd get the 32-bit limit, we'd shift 1 with 3, so we'd get this bit right here. We would and this with this. So if this x was a 1, then it would return a 1. If this x was a 0, then when we and we get the value of this, it would be a 1 anded with a 0, this would be a 0. So we're just, you know, returning a 1 or a 0 from here. So this doesn't need to be void, this needs to be like uint8. Alright, so I will have, after that, those are only 3 simple one-liner functions here. I will have a function to find, when we go to actually allocate memory, when we go to allocate memory, I'll have to find the first sort of chunk that is free. So I'm going to have a function to find that. Find the first free area of memory. These will be free blocks, effectively. So find the first free blocks of memory for a given size. And the way other people have done this, they return like a -1 or an error status or whatever. I'm going to return, I guess, a -1 for some of these to signify an error. So that's why I'm making this a signed integer, not unsigned. Otherwise, it will equal the block that is free, or at least the start of the region that is free. Call this find first free blocks. This will be a 32-bit, have a number of blocks. So if we say, if we've calculated however much we need to get, and we say, okay, this file is like 4 blocks in size, it's like 16K. We need to find a 16K region of memory that's free. So we call this and see, okay, we need to check if there is that much space is free. Wherever it starts at within the memory map, we'll return that byte or bit or what have you. So first of all, if they passed in a 0, we're not going to do anything. I don't know why it would, but maybe sometimes this would. Can't allocate nothing. Can't return no memory. Otherwise, for performance's sake a little bit, we'll test 32 blocks at a time. So I'm going to have a loop to loop through all these blocks for I equals 0. What is this? I less than the max. Okay, so we'll start at the front. However many blocks we have. This is not really a really good performing memory manager. This is mostly pretty simple so that I could understand it. So keep that in mind. Not the best performing thing. So I is going to go through the max number of blocks that we have divided by 32. We'll figure out the max number of blocks later, just right now. 32 blocks at a time, because I can be a 32-bit integer, and each 32 bits will be 32 blocks that we're handling, because we're doing a bit map. So okay, for each I here, until we get to the maximum limit in the number of blocks we have, which will be the end of allocated memory, if that area within the memory map is not equal to all f's. So later on when I initialize the memory map, I'm going to set everything as used. So every bit within the memory map will be 1. So if we have 32 ones in hexadecimal, that is, 8 f's here. So basically, if we find a region of memory that is not set, so if all the bits are not set within this, 32-bit region of memory, then we know at least one bit in here is not set. So we want to see if starting at that not set bit, if there is a free amount of memory, you know, corresponding to however many blocks we need, however many bits we need. So if we have some region in here that's not set, I'm going to put at least 1 bit is not set within this 32-bit chunk of memory. So find that bit by testing each bit. So we need to find which bit is not set and then see from that bit if we have enough free memory, if we have enough bits that aren't set to correspond to the number of blocks that we need. So we'll have another loop. Nested loops are fun. So for j equals 0, j less than 32, j plus plus. Not sure this has to be a 32-bit, but that's what I had it written down as. I'm going to set a little bit variable here, which will be 1 shift left by j. So j will be 0 to 32, or 0 to 31. 1 shift left by this will get the bit within the memory map, you know, whichever bit is not set, and we're going to test each bit. So if bit is unset or 0, we found start of a free region of memory. If not, I don't need caps. If not, memory map I, or j, no, it's I, sorry. If we AND with that bit, it'll return a 0 or a 1. So if that bit is not set, if not, memory map I ANDed with this bit we have, I shift left j. Then we found the start of a free region of memory. This bit is not set within the memory map. We need to see if, you know, we have a chunk of bits that aren't set that correspond to however many blocks we need or not. If not, we'll keep searching, you know, for the next chunk. Okay, in 32T. Okay, so I'm going to have a start bit or a starting bit, which is going to be I, working with 32 at a time. So I times 32 plus a bit that we set here. So this is kind of indexing the memory map. So we're getting that ith indexed bit here. So I, in this upper loop, will point to each 32 bits, basically, within the memory map, because it's 4 bytes. Within that 32 bits, we're getting the bit j. So we have to multiply this 32 bits by 32 to get the overall, you know, chunk within the memory map. We'll add the bit to that to get the bit that is set off here. So it's kind of indexing the memory map for I to get that bit. I'm gonna have a thing. If we don't get here, if we do get here, we'll have free blocks. So I want to see how many blocks are free starting at this bit to see if we have enough space. Count equals 0, count less than num blocks, or is this free? Yeah, num blocks. I'll have a counter to see if we have enough free blocks for this space. So we can test the block starting at the starting bit, the start bit, rather, plus count. And if so, we have more free blocks. So since test bit up here returns a 0 or a 1, if that bit is set, the first one won't be. So, I mean, for the 0, this should work, but basically we're starting at this bit in the memory map. So we want to test if each bit right after that bit is set or not. Because if we have enough bits that are not set, like if we passed in number of blocks 10, we want to find 10 bits in a row that are not set, because that will correspond to 10 free bits within the memory map, and that's 10 free blocks that we can allocate. So we have, you know, I'm just having a little counter here to count up to however many blocks we passed in. If each one right after that starting bit is not set, we're going to increment our free block count. If it is set, then we'll reset and come back here sometime later. This will be reinitialized to 0. We'll start over again. But if it's not set, we want to increment free blocks, and then we want to test if we found however much memory we were looking for here. So free blocks equals the number that we passed in, you know, then we're good to go. If we did find enough free space, I'm going to return that bit within the map, which again, to index it from I, I'm going to do I times 32 and add j to that. So j was our original bit that we started at up here. The first bit that was not set within this region that we searched for. So starting at this bit, j, we've found a region of memory that contains at least this many number of blocks that are free. We want to return that region. That is what this is doing. Okay, if we went through all of our memory here, so we went through this whole loop and we haven't returned anything, that means we don't have enough free space within the memory map. So I'm just going to return a -1. No free region of memory large enough. Get that back. Okay, so that's finding the first free block of memory, first free blocks. Okay, to initialize, I had a function to initialize the memory manager. So let's write that out. Initialize memory manager. 32 bits size and 32 bits start address. I'll switch these around just to be different. So I'm going to set the memory map here, this global variable that we have up here. I'm going to set that to, our size. It's a 32-bit pointer, so I'm going to make it a 32-bit pointer to the address that we passed in. That's where the map is going to start at in physical memory. And then I can set the other global variables, the max number of blocks and the used number of blocks. So the max number of blocks to start off with is going to be however many blocks of memory we have from the size that we passed in. We'll have whatever size we passed in divided by however big our blocks are, which are 4,096. So if we pass in like, I don't know, 10,000 in hex or whatever, we'll have that 10,000 in hex divided by however big a block is. That'll give us the maximum number of blocks that we can have for this memory manager. That's what that's doing. The used blocks, I'm just going to say to start off with, every single block is going to be used until we free or initialize some regions. So to start off with, this is going to equal the maximum blocks that we have. So to actually set all of these blocks as used, so that set all these bits as 1 effectively, so that we can do these checks, like for finding a free region. If it's not equal to this, well, we need it to equal that first before we can find something that isn't equal to that. I'm going to do that with a mem set, just to set this whole region of memory that we passed in. Starting at this start address, I'm going to do a mem set it all to all 1s. So I'm going to pass in the memory map, which is pointing to the start address. I'm going to set everything to FF255 so that every 32-bit chunk in here is, all 1s. Although this is just 1 byte because our mem set works off 1 byte at a time. How many times do we want to do that? It'll be max blocks divided by the blocks per byte. So I am using that blocks per byte define up there. So this is 8. So it's max blocks divided by 8, and that will give sort of 1 byte, 8-bit chunks that we're going to set all to F, within the memory map. Effectively, everything will be Fs. It'll just be 1 byte at a time. That's what this is doing. So the length that we're going to set is this many. Okay, that should work. But for this to work, if we pass in a large region of memory, then memset is not going to work because it only has a 16-bit for the length. So I'm going to change memset actually. That would be B7. So at the bottom here in memset, I'm going to change the length to be 32-bit because if we want to set, 32-bit number of memory, then we need that to be 32. Also, our I needs to be 32. So that should work. So later on when we set all of memory, this will work and not error, or well, silently error pretty much. It'll set all the memory. If we pass it a giant size, that should be okay. But after we initialize the manager, set everything is used, I want to initialize some parts as free, so I'm going to have another function for that. Well, this will be for initializing a region of memory. Sets blocks as free or available. So void as well, yeah. Initialize memory region. I'm going to pass it a base address to initialize from, and then a size of memory that we want to initialize here. I called this a line because some tutorial had that, but basically the base address divided by the size of a block is going to be where we start the initializing from. So this will convert the memory address to blocks by dividing it by the block size. So if we pass in like 10,000 in hex, it'll divide it by size of a block to get the correct block within the memory map that we're going to start initializing from. Then the number of blocks that we need to initialize comes from converting the size that we pass in to the block size. So I'm also assuming this is at least one block of memory. If it's less than, this will be like 0. But I think that might still work for this, so we'll see how that works later. So that'll be the number of blocks we want to initialize, starting at this address. I'll have an empty initializer and a for loop. While the number of blocks we need to initialize is greater than 0. This is just one way I did it, twice minus. So I'm going to set the block that starts at that align variable here. So the starting address, we need to set it, or no, we need to unset it, I'm sorry. If it was set, it'll be unset. So to free the memory, to set it as free, we need it to be a 0, so that'll be unsetting the block. Then I'm going to set the used blocks as 1 less. Since we just freed a block, the used blocks will go down because we just unset it. So afterwards, I'm always going to set separately first block to ensure that we can't allocate a 0 and can't overwrite stuff like the interrupt tables, you know, IDT or IVT, BIOS data areas, and other things that we don't want to set. So I'm going to do set block 0 at the end of this. And we don't need to do that every time for everything. That's kind of wasteful, but to make it simple, we can just do this here. And then 0 will hold the first block. This will be setting the first block in memory from address 0 to 4096, which is 1000 in hex. So everything below 1000 will be set, so we won't be able to overwrite, you know, the interrupt table at the start of memory, or the BIOS data area at the start of memory, and anything else we put up until 1000 in hex, that'll be safe from doing this. But if we have an initialize function, then we should also have a corresponding sort of deinitialize function. So that'll be here. It'll set blocks as used or reserved. Again, given the address and size, be deinitialize. These will be the same. Everything will be the same, except this will set the block instead of unset, and used blocks will go up instead of down. We will not do this. If we want to allocate one chunk, we can deinitialize the whole chunk, set it as used, and we won't be able to overwrite that later on. So that's what that's for. All right, there's going to be 2 more functions, and then we'll be done. This will not be a particularly big file, just like maybe even under 200 lines, I think. But how do we actually allocate and free the blocks of memory that we're going to be, you know, using these other functions for? Even though the kernel will use this initialize stuff, but how do we do that? Well, I'm going to have a couple of functions for allocating and freeing blocks of memory. I have a uint32 pointer called allocate blocks. We'll pass in a number of blocks we want to allocate. So num blocks there. So first I'm going to see if the maximum number of blocks minus our used number of blocks is less than or equal than the number we passed in. So if we're searching for 10 blocks of memory that we want to allocate, if there's not 10 blocks of memory left to allocate, then that's what this check is for. We're going to return and say, hey, yeah, we don't have anything left. So return 0. No more memory left to allocate. If this is basically, this gets the number of free blocks that we have. So the number of max blocks minus the number of used blocks is the number of free blocks, the blocks that aren't used. If the number of free blocks that we have is less than the number of blocks we passed in, then we can't allocate that number. It might just be less than, because if we had 10, we should be able to allocate that, right? Unless we always wanted to keep one free. I don't know. I'll keep less than or equal. I don't know if that's a bug or not. That's what I had before, but otherwise, I'm going to get a starting block that we're going to allocate from. This will equal find first free blocks, that return value. We'll pass in the number of blocks. This doesn't need to be uint. Number of blocks. So this up here if we find, the free region, this number of blocks that are free, we're going to return that down here because we want to allocate that. And if that is -1, then we could not allocate that, or we couldn't find that many free blocks. So yeah, effectively we can't allocate it, but we couldn't find that many free blocks to allocate. But if we could, then we did find that number of blocks. And if we did find that number of blocks, since we're allocating them, we're going to set them as used so that no other process can allocate the same blocks, because that would overwrite them. I don't want to do that. This is for whoever's calling it right now. So I'm going to set them as used. So for I is 0, I less than number of blocks. So I'm going to set these blocks starting at the starting block plus I, which will start at 0. So all these blocks that we set, that we found, all the blocks that we found, we're going to set starting at the starting block for the starting region of free blocks, and then I up to the number of blocks. That's how many are free. So if this is like 10, we're going to, set these 10 blocks that we found from this function. And that'll look it up in the memory map. So those 10 bits effectively in the memory map will be set because we're calling set block. So those 10 bits will be set from this. And that's a one-liner, so I don't really need the curly braces there. So after that, the number of used blocks will go up by the number that was just set, plus equal num blocks. And then we want to get the address to this region that we allocated. So address is the starting block times the block size. We have to convert it into blocks, or convert the blocks back into bytes rather. Since each block is 4096 bytes, each block handles 4096 bytes of actual memory. So the starting block that we had, if it was block 10, then the actual physical memory that block 10 is, representing is 10 times 4096. 4096 times 10. That would be the actual address in our physical RAM that we have started allocating virtually here. So we want to return that address because in our manager, we're saying it's being used. So that actual physical memory address, we're converting basically bytes or blocks to bytes. Okay, we want to return that address. So I'm going to return a 32-bit pointer. Other sources used a void pointer, which might be applicable in other instances, but I'm returning an actual pointer just to not have a void pointer here. We can change that later to 64 as needed. Right now, we're only working with a 32-bit address space, so I'm going to return a 32-bit pointer to this address, and that'll be the physical memory location. All right, so does that make sense? We allocate the number of blocks that are free within our memory map, which is this sort of abstract 32-bit, pointer to an area in memory, wherever we initialize the memory manager at. That just holds the map, but the map physically points to each block, each bit in the map. Well, not physically points to, but represents the physical address, 0, 4096, 88192 rather, every 4K. So we return, whatever 4K actual physical address was being allocated here. So that's how it converts the bytes, it converts the blocks to the actual bytes in RAM, and we're returning that address in RAM so that it works. I just want to, that's kind of the bulk of what we actually wanted to do here as far as allocating memory. But the counterpart to allocating is freeing memory. So I also want to have a thing to free blocks of memory. It'll be void free blocks. Instead of allocate blocks, we'll have the address again. So given a physical address, I'm going to free blocks at that address, however many blocks we pass in to free, which will unset them in the map so they can be reallocated later. So I'm going to have a starting block again, which is going to be the address. We're going to make it a regular integer, not a pointer. Although I'm not too sure I have to do this, but I had it casted anyway. Okay, so this will convert the address to blocks. because the address will be in bytes. So we divide that address by the block size because it will be on block size boundaries. Since when we allocate, we return however, 4096 byte of RAM that we've allocated from. That guarantees that all of the allocated addresses will be on a block size boundary or a 4096 byte address. So to easily convert that back into blocks, we just divide by however big our block size is. So we divide by 4096 to get the right block that this number corresponds to, because this is basically a multiple of 4096 for the actual memory address. So that makes it, kind of easy. And then we want to get however many blocks that are in there, and then we want to unset them. So that's what this loop will be for. Start at 0, we'll go up until the number of blocks. I'm just going to unset these blocks. If I can do an underscore, there we go. Unset block. Starting at the starting block. And then we'll add I, because it'll start at 0, it'll go until here. So if we allocated 10, we now want to free 10 blocks of memory. We'll get the start of that 10 blocks of memory, get the starting block, allocate 10 blocks, offset from that starting block. And then after we freed those blocks, we can, instead of adding to used blocks, we can subtract from used blocks the number that was just freed because they are no longer used. They are unset back to 0. The bits are unset back to 0. Okay. Do decrease used block count to increase count. Okay. And that is our whole physical memory manager. It's not very big. It's 146 lines approximately with free blocks, allocate blocks, initialize, deinitialize regions of blocks, initialize the memory manager to begin with, find a region of free blocks within the memory map and see if that block is set or not. Otherwise we can set it or unset it. Those are the base amount of functions that we need for this to work. But it's not that many. Assuming I typed it all correctly, we can go on to use it within the kernel, and if I didn't, then I'll debug. But that's all we have for the physical memory manager header file. So I will add it to the kernel. I'm using memset, so it should probably go before or after string. That would be after string. I'll put it like, I don't know, up here. If it gives me an error, I can move it around. Next, I will initialize the memory manager and print, the info about the number of blocks that we have. I'll print that to the screen. So I'll do that stuff next. Okay, so now that we have the memory manager file and the header made, it's included in the kernel, I'm going to initialize sort of the memory manager within the kernel and print out the memory block info that we got from that. And I'll add that to the print memory info function as well. But right before we do that, I did have a small issue here in which I misplaced an S or whatever. On the file down here, it's supposed to be block, not blocks, because I put block right there, so. Figure that made more sense. We're unsetting, starting at the starting block, not the starting blocks, so that was just a small thing. And that kept it from the make command running. So we'll have to increase those sizes. But I'm going to set up the info in the kernel first. So at the bottom, we have this file included, right? Yes. Okay. So at the bottom in the print physical memory info function, where I have down here, print total amount of memory, print out memory manager block info. That doesn't need to be a to-do. So I'm going to print out the info, the total amount of memory in blocks. So in 4 kilobyte blocks, it'll be the total number of blocks, which is what that's going to be. Total number of used blocks, and free blocks, which are not used. So I'll print out something like total 4KB blocks. Right now we only have print hex, so it'll be in hexadecimal for all this. I can just do this, I don't have to do that. Kernel cursor X and Y, so this will be the max number of blocks from the header file we just did up here, the max number of blocks. And that's static, but it's only included in the kernel right now, so it'll be visible in the kernel. So we'll have it available here. Okay, so let's get the used or reserved blocks, which would be the used blocks number. I'll probably put this on the next line, so this will be a new line delimited. Used or reserved blocks, these will be used blocks. And then we'll have, I guess I'll just copy that. We'll have free, or since that's counted as hex, we'll have to do that, free or available blocks. And this will be the max blocks minus the used blocks. Used or reserved, free or available. Oh, I got rid of the first one, didn't I? Yeah, that's my mistake. We'll have total 4 KB blocks. This will be max blocks. So max blocks, used blocks, and max minus used. Then I can probably just print out like a new line or two. We'll do 2, I guess. Separate it out from everything. I'm going to see if I need to like null terminate these. I'm pretty sure I do. But in some cases, maybe I don't. So I do want to see if I need to or not. 19. Answer that in a second. So I got 19, which would be 3 more. And then this would be 3 more, which would be 30. I need to change that in the boot sector as well. Do that 18 though, because it'll be 19. See what that prints out. Okay, so there we go. Total memory in bytes, again, is the 4K limit there, or the 32-bit limit, 8Fs. Total 4K blocks, I have 0. Oh, that's not good. Used or reserved is 0, free or available is 0. Okay, these are 0 because we haven't actually initialized anything in the physical memory manager. I'm printing out info, and they're still initialized. They're not being used yet. But I did want to see that they actually have values, so that's good. I will go ahead and initialize it in the kernel. Let me do that. I'll probably do that before we actually go and put stuff in from the user. I know I'm printing the info here. If I'm printing 2 new lines in here, then I don't need that because it's automatically going to do that at the end. Let me initialize it first. Initialize physical memory manager. I'm going to have probably a num entries like variable again, or maybe just call it smap entries or something. Which means I need one because I don't have it as a global. That's okay. Let's make smap entries. Number of smap entries. That's all that is. Okay, and this will equal smap entry t pointer to that location of memory that was in the bootloader that we put the smap at, physical memory map, which was 8500 for the number of entries. 8504 again is where they're going to be read from. So I'll probably make that as well. In my test OS, I had global variables, but I don't in this, which is fine. It's probably better to have local. I'm just going to do that then. That'll be a pointer, actually. Pointer to an entry. This will equal... This one won't be this. This will be a uint32. Mine's a little scattered. Apologies. Smap entries is going to be a uint32, so I need a uint32 pointer to this. Okay. Yep. But then the smap entry itself for this struct up here, this will be, you know, this sort of data type at the location of memory, which is 8504. Yeah, there we go. That's the starting entry, basically. I'm going to initialize the memory manager sort of for all of our available memory. So to get, you know, the max amount of memory, how we did in the function down here, I took the last, basically the last entry right here, the last entry, and added these things together. So I'm going to do, you know, pretty much that. just get the info from the last entry. But to get the last entry, I'll have to add number of entries. This is not a good name for this though. Let me rename this. Num smap entries. That makes more sense because then they both don't look like the same thing because they're not the same thing. That's probably a little bit easier to understand, hopefully. So this will plus equal the number of smap entries minus 1 because it's going to be 0 based. The number will be 1 based. This will be 0 based. Okay, then we'll take that base address plus the length minus 1. That'll give us a total amount of memory, which is, you know, a 32-bit limit. I'm probably going to put that into a variable as well. I'll put that up here. I'll call it total memory. Instead of printing that, I'm going to make it equal. Delete all this. We'll make it equal to the smap base address plus the entry length minus 1. And then we're going to initialize the physical memory manager with this amount of memory. Physical memory manager, I'll do setup, and then we'll do initialize. Initialize the memory manager to all available memory that we, got from the total memory there. Put it at some location. So all memory will be set as, it'll be set as used or unavailable or reserved. Use or reserve by default, and then we'll initialize the regions later with those functions that we put in for initialize and deinitialize region. Initialize memory manager, I should pull it up. All right, it was here. Initialize memory manager. So start address and size. I'm just going to put it at, right now, just an arbitrary memory location. Doesn't really matter. I'm going to put it at 30,000, just so I assume it's out of everything else's way. I need a base address and a size. So that's the address. I'll stick it at 30K right now in hex. And the size is going to be total memory. That's the amount of memory that we're giving it to initialize. It's all going to be set as used. Start address and size. This will memset everything to 1. So basically the 4K amount of memory and size in blocks. So it'd be like divided by, 4K and divided by 8. That many blocks starting, or that many bits, whatever, starting at this memory address will be set to 1 for our memory map. So our memory map, variable here will point to that location in memory, and it'll be sort of managing the 4 GB memory limit from that location. That'll be the base address of the memory map. So now I'm going to initialize the memory regions for the available memory. So everything that is a type 1 within the memory map entries, I'm going to initialize those. Type equal 1, which is available. So I'm going to reset this to the first one and then read through all of the entries. So basically, I'll just reset this here. Do I. So I is 0. I will be less than the number of entries, or number of smap entries. I plus, and then we'll just check if the type is 1, then it's available. So we can initialize that memory region. So we'll call it initialize memory region, which takes in a base address and a size. So then we can just pass in the base address and the size from the smap entry. Needs to be underscore. All right, base address and size. Or is it length? Length, okay. Gotta have like 2 names that are basically the same but different. So pass it that. That will initialize all those blocks of memory in the memory map, which is at 30,000. It'll initialize however big our region is in blocks. So it'll unset all of them because they were set from memset. They were all set to 1. This will call unset block for all of those that are free, and it'll mark them as free by setting those bits off back to 0. But then it'll set the first block by default, 0 based, so 4096 bytes, so 0 to 4095, approximately 0 to 1000 in hex is going to be set as used by default after we initialize any region, just to make sure that we don't mess with the interrupt vector table or descriptor table, BIOS data area, whatever else is there. We might put stuff in there later for the kernel and stuff. So as long as that's not messed with, then we're good. So we did that. So we're initializing them all to free. I could also probably do smap entry ++ in here. Otherwise, I could do it after this if statement, but that's fine. We'll just do that. And actually, these are both one lines, so we can probably just do that. Save a line, but okay, after we initialized everything that's available to us, we can also de-initialize stuff that we don't want people to mess with, such as the memory map. We only want the memory manager to mess with that. We don't want user programs to be able to overwrite this memory later. That'd be bad. So that will set off, and any other things we can set, like any memory areas we designated for the kernel that we don't want user space writing over, even though we don't have a clear distinction or privilege level difference or anything right now. Later we might. We want to protect those things in memory. So I'm going to set certain memory regions and blocks for the kernel and any OS memory map areas. I'm going to set those as used or reserved, which will be a call to de-initialize memory region instead of initialize memory region. Yeah, de-initialize takes in the same thing, base address and size, and then just sets the blocks instead of unsets them. So sets them to 1 instead of clearing them to 0. Since by default initialize memory region will set everything up to 1000 in hex because it sets block 0 every time, anything upwards or in addition to that we want to de-initialize here. So I have used some areas of memory up through 8000 or 9000 in hex. I'm just probably going to initialize everything below like A000 as used, just so we have, you know, a tiny bit of buffer space. We'll probably expand that later, but right now that's all going to be for the kernel. So starting at 1000 and going 9000 in hex, you know, that's the size of memory we want to de-initialize starting at this address. So basically everything from 0 to A000 is probably just going to be set as used here. We'll say reserve all memory below A000 in hex for the kernel/OS. And then I'm also going to de-initialize the region for the memory map. How much memory is that taking up? I don't want to overwrite what the memory manager is doing. The memory manager is located at this region, right? And that does a mem set for all the blocks, starting at that start address. So that's probably actually okay. I'm just trying to think, do I want to set everything as used, like for this, but the memory manager automatically does that. We just have to make sure we don't dole out memory at this space. I'm not going to do that actually. I was going to say we need to reserve where the memory map is at in memory so that other things don't override it, but the memory manager is ultimately, and the kernel is ultimately going to know, it should know, you know, not to overstep things. And we'll dole out memory to programs as needed, and we'll make sure that that does not include the memory manager area. It might be better to just make that like a constant or a define up here, just in case. So I might do that. Or a define. Yeah, I'll make it a constant. I'll call it memmap area. UN32. Okay. I'll do that. I should be making more constants for things anyway. We'll have those things. I will put more constants here eventually. Constants. Fill out more constants to replace magic numbers, because that is what we want to do. Okay, so that should initialize the memory manager and a region of memory, and de-initialize a region for the kernel. So that's all good. So after that is all done, I'll print out a string that basically says, hey, we initialized the memory manager, all is good. We reached this point. So I'm going to call it physical memory manager initialized. I can put like a couple new lines. I think I put 2 before, yeah. So 0A, 0D. Okay. And then we'll call and print the info after that. Successfully set up and initialized physical memory manager. So after that's all set up, we'll print the info. So at the end of this, it should have updated numbers for max used and, free blocks that it prints out here. So let's see. That might take up more space. I might have entered something in wrong, which I did. Uint32T from a pointer. Did I make that a pointer? No, I dereferenced. Okay. In my notes, I want to dereference this. Yeah. I want to get a pointer and then get the 4 bytes at that pointer at that address for the number of entries. That would be correct. And this is still 190D1E. Okay, so let's see if it breaks. No, I think we're good. We have this number of 4K blocks, which since 4 kilobytes is 4096, in hexadecimal that is 1000 in H, so I guess it would be 3 less, right? And it is 3 less. FF. Okay, so that's 1 megabyte. So we have that many 4K blocks. The used or reserved blocks, we have that F8089. That's, majority of it. And then it should be 5 Fs minus this number. 1, 2, 3, 4, 5 minus 8089. 7F76. So that's correct. So we have about 32,630 free blocks that we can mess with. Now that is not including the blocks in the memory manager, although I think it is actually, because we set all those. I forget, but we have that info available, so that's good. Let me see. So I know we set these, but I don't think I just set used to be the max. So this used count and max block count it is assuming that we're using all of the blocks by default that we pass in for the memory at the memory manager. So all of memory is set to used. So that means all of the blocks for our memory, all those bytes, are going to be set for used. So I was trying to, I'm trying to think again if I'm doing this right or not. If I need to explicitly set the memory manager's, area and memory as used blocks, but I think it's already set as used blocks from doing this. If it's not, then I'll go back and do that later. I'm just not thinking the most clearly at the moment. That's okay. I got other distractions. But we did initialize it. We do have valid used and free and max block counts. That's good. And probably need to go ahead and allocate blocks to a program and then load it to memory and then free it when it's done, with the physical memory manager, with allocate and free blocks with these functions down here. So I'm going to go ahead and probably do that next. Okay, all right, before I go on, I did add one more new thing here. I did actually deinitialize the memory region for the memory map. Since it was all initialized here from the initialize manager function, we then went on to initialize the whole region, and the first region that was available would be the first 640K, of which 30,000 in hex, where the memory map is located within that first initial 640K. So that would be initialized to zeros or free memory, and I don't want to do that. I don't want other things overriding the memory map in memory, so I kind of deinitialized that here just to make sure that didn't happen. And since the manager's initialized for the maximum number of blocks divided by the blocks per bytes, that's the actual bytes that the memory manager takes up. So starting at 30K, it would be this many bytes that would be taken up by the map. So that's how many bytes I have here going into the deinitialize region function. So that'll just set all of those as used for the memory map so that nothing else can overwrite that data. So that's all, I just added that there. But going on to actual new things, to allocate in free blocks, I'm going to put that after all these commands that we're not using. Here where load file is, so right after, I guess, the rename command here, I'll put this stuff. I did want to make one other command actually, and it'll be for prtmemmap, so I'll put that down here. I can put it there, I'll call it command prtmemmap. I'll do string length for it, same as the others. it's just going to print out the info that the current function down here does, the print physical memory info. It'll be doing the same thing for that. But I'll put it here after these. It'll be here, and it'll be called prtmemmap. And this will print physical. I guess I can print all the info, so maybe print physical memory info would be a better command, but I called it prtmemmap at the time, so I'll just call it print physical memory map info. In my test OS I called it that. It'll call this function here physical memory info right now. So I can give it a better name later. So I need like a print string line, or I'll just write it, it doesn't matter. Kernel cursor X and Y. I'm going to prep in this with new lines. I'm going to write out physical memory map. I'm going to precede that with like dashes for like the header style I've been doing. So that's PHYSICAL space MEMORY space MAP. So that should be alright. Then I'll have 0A, 0D, so that'll print, you know, dashes, new line, this will be on the next line. Okay, and then we'll continue it. Another new line. Same dashes here. And then I did 2, okay, 0A, 0D. Alright, and then I'll just call the print physical memory info function. And then we'll continue. So all that's going to do is just print out what we already have. So that's like a way to sanity check and test between function calls or loaded files if we're actually freeing and allocating the blocks that I say we're going to free. So we can check what the info is if the block amount changes, you know, or the memory changes somehow. We know something's probably wrong. So there's that. I guess I can test that right quick. And see, it should just print out this info again. So we do something like directory. Let's print out whatever, it doesn't matter. File table. So prtmemmap prints out physical memory map. Got that header. I missed one dash, it looks like. That's alright. And it just prints all these out again. So this should be the same because we did not load anything. And that's true. Okay. Prtmem, there we go. I'll just add one more dash there. Okay, but I'm going to actually allocate and free the blocks now. I'm going to change this code here. So we have a text file pointer right now, right? I'm going to rename that just a regular file pointer because it's going to be generic. So I'm going to test, or I'm going to set file pointer since we have the file ops header included. Since we have the file ops header included, we have access to that, to the function down here, check file name. So I can check this from the kernel if I need to, or from whatever other file has that header included. So I'm going to do that here and set file pointer equal to this just to see if the file's there. That way we can get the file pointer equal to the entry in the file table, and we can check, well, mainly for this, what the file size is in sectors. And then we can convert that file size into however many blocks we need to load the file, and then use that to allocate that many blocks to then load the file to that address after allocating. So I'll get to that because that might not make sense right now, but we'll just call check file name. We're going to check whatever the user entered, which is in command string, or I guess in tokens, but I had it as command string. And then we'll do tokens length. The first one, because that is the first token for whatever they're doing. If they're loading file table, this will be file table, and then the length, however long that is, which is, you know, 9 or 10 characters for that string. So if it points to 0, it did not find it. So I can check that there. I guess this could be null as well. I think that's equal to 0 in C. Maybe that would make more sense here for a pointer. But if it's null, assuming this works, I'm going to print out something like it wasn't found. So the failure message, we have that, we can appropriate it. This will be file not found in file table. We can error. So the failure message here, command program not found, that's what I'm doing. We're not loading it, but we didn't find it, so we can use that message. Then I'll move the cursor after that point. Then we'll continue. Okay, but if they did find it in the file table, then file pointer at this point will be pointing to that entry, so we can get the number of blocks needed to load the file. Let's say num blocks will equal the file size in sectors times the number of bytes in a sector, which is 512. It'll be divided by the size of a block in bytes. Okay, so the file size times 512 will get the file size in bytes, and then we divide that by the size of a block in bytes, which is 4096, or the block size, constant we have. And that'll give however many blocks we need to load the file. That'll give the size of the file in blocks, converted from the size in bytes. So I'll put like needed blocks or number of blocks, how many blocks we need. So this is going to equal the 15th byte offset from the file pointer, because that is the 15th byte in the file entry. Like if we're loading the file table, the file pointer will point to here if we found it from the check file name function call. The file size in sectors is here at byte 15. So then multiply that by 512 or whatever our bytes in a sector is. That's another magic number I need to change. And then we'll divide that by the block size. Actually, no, I need parentheses around here. That's why I did that. There we go. So that'll convert file size in bytes to blocks. And if it's less or only 512, maybe it's 0. I don't know why it would be, but if it is 0, well, it could be 0. If it's less than 1 block, it'll be 0. So if the file size in sectors is less than 8, because 8 times 512 is 4096. If it's less than 8, it might be 0. So if it's 0, we're just going to make it 1 to prevent any errors, because they need at least 1 block regardless. If file size is less than 1 block, use 1 block default. Alright, so then after that, I'm just going to print out some info. Copy this down here. I'm going to print out a little new line. And we'll say we're allocating a certain number of blocks. So I'm going to put allocating. This will still be in hex. I am going to make a print decimal function after I make sure this is working, just so it reads a little bit easier. But we'll do this for now. So I'm printing that many blocks, put a space because they'll have the number. Or no, this is going to be after, sorry. This I need to put here because we're printing a number out. This will be needed blocks. Then we'll put in after the number, I'll put a space. It'll be that many blocks. If it's only 1, it'll be a block, so I'll put that in the parentheses. That many blocks. And then we'll load the file or run it. I'll put 2 new lines here just to have some space. So that'll say we're loading this many blocks to the screen for this file. Then we want to load the file to that address. But we need an address to load it to, and that is what the call to allocate blocks will do. Down here it will return an address, the physical address in RAM where the blocks were allocated. So we can just call allocate blocks for an address. We do have this needed blocks here, which is going to be a variable. Let me go ahead and add these while I'm at it. It could be maybe 32, so I'll just do that. Needed blocks, and then I'll add the address is going to be a pointer. Allocated address. Maybe that's straightforward enough, I don't know. Okay, so allocated address equals allocate blocks, however many blocks we need, needed blocks, B2. Let me just make sure. Yeah, we just pass the number of blocks. It finds the first free blocks if there's a region free with that many blocks that we need, and it'll return the address in memory, actual memory, to the start of a region of that size, of that many blocks. So if we need one block to load a text file, like the file table to the screen, then we're going to load one block somewhere in memory, and the address to that block in memory, that 4096 byte chunk, is going to be this address returned from this function. So allocate 4K blocks of memory, get address to that memory, and then I'm going to say we allocated that, just to make sure, as a sanity check. I'm going to put allocated to address, and then we'll do the allocated address. And I don't think I need to cast this, but just to make sure we're getting the value of the address, I'm just going to cast it to a 32-bit. We're getting like an integer value. If the address is like 10,000 in hex, this will return 10,000 in hex. It won't, you know, I don't think I need to do this, but just to ensure I know that it works, so I'm casting it. But you may not need to do this. But we're allocating to that address, and I'll do another new line after, because I did that before. Okay, then after we're sure we've allocated, we can load the file. So I'm going to leave this for now and just make sure that this message pops up and that it's good. See if we can still make, which we can't because I'm calling text file pointer. So text file pointer. This just needs to be file pointer. I'll make sure that's true for all of these. Okay. And we don't have null defined, so never mind, that'll be 0. Eventually I'll probably just define that as 0. And that is now 1A, which is perfect. 19, 1A, which is 1 more than 19, so that'd be 2, 4, and 3, 1. So 1.8 will now be 1.9. And this will be 1A. And eventually I do want to improve that as well. A lot of things I want to improve, a lot of eventuallys going on here. So we load the file table, that should be one block that we allocate. So we allocate 1 blocks. We've allocated that to address 20,000, which I don't think I need to go that far, so that may be a bug. I don't think I need to go that far to allocate. It should only allocate it like A000 to start. That doesn't seem right. I'll have to look at that. But anyway, we did allocate to an address. We did load it to that address. So now if we do prtmemmap, we should be 1 block less, 7F56 instead of 57. So right now we technically have a memory leak because we're not freeing that memory when we return. So I do need to do that as well after we return. Or do I want to see why this is 20,000? I figure that should be A, right? Because we did 1 to 9,000. So after this, we should have A000, or if I was 1 off, B000 should be free. The memory map starts at 30K, so why would it be 20? I'll worry about that later right now. It could be from doing this as well. I am just curious, so I want to see what happens if I do this. So now we have 7.6. That does make more free. Now it still allocates to 20,000. Okay, just wanted to make sure that didn't have an effect. And it doesn't. Which is interesting. We're only setting the first block though. It shouldn't set all the way up to 20K. That's not good. But I will look at that later. I will put that down here as a to-do. To-do. First free location seems to be at 20,000. Find why. Is this wrong? Should be at A000. Okay, I'll leave that there, but we'll worry about that later. Right now we can actually load to this address. Since we allocated it, we can load things to 20,000 instead of, you know, hard coding 10,000 here. Okay, this 10,000 we can change. So I'll make it the allocated address again. Since we weren't passing a pointer, we were passing a value to load file. So instead of hard coding to 10,000 every time, we'll code it to whatever was returned from allocating the blocks. That'll be dynamic now. It's not hard coded, which is good. And it should load to that address and be okay. All right, so the same thing, if it's not a binary file, I also want to load it here to the address. But since this is a void pointer, it'll be a pointer, not the value, so I don't think I have to cast this to a regular uint32. I can just use allocated address. That should be all right, but we'll change it here so that programs are loaded there, or regular file, well, regular files are loaded there, so we have to do this because it's going to be loaded to that. Otherwise, loaded programs would not run. Same thing here. Allocated address. That way text files can be read 1 byte at a time from that address that the file was loaded to. So that'll be good. So the only thing left, if this works, would be to free the memory. I'll do that like here. Free memory when done. So this will be like a call to free blocks, I think. And then we'll do the same for the text file down here. Free it when done before we go back, but I'll leave that there. We'll see if we can allocate and load stuff and still run things first. So if I go file table, it should have loaded it to this address. It read it from that address, 20,000, allocated 1 blocks. We're not freeing it yet. So again, this will go down by 1 from what it was. That's okay. The used blocks also went up by 1, so that's good. All right, so if we load something like the editor, that'll take up more than 1 block. Let's load the file table within the editor. I didn't do that right. Also, these strings are wrong. That's okay. There are some issues with loading strings now, but I'll get to that. We go back, and it didn't quite jump back correctly either, which is interesting. So there are still some things I have to look at, but I think that would have loaded all right. I'll see if calculator works. It did allocate a block. So we would have gone down by 1, yep. And that would have gone down by another. Okay. That seems to be working all right. We can run programs, although sometimes they're a little buggy. And I believe that's partly due to the linker files I have. So these can change now. The calculator and editor linker files, they shouldn't be loaded hard coding 10,000 anymore. Now it's loaded to wherever is available. So I can get rid of that, simplify this a little bit for the calculator and the editor. Just get rid of those hard coded 10K. The kernel, probably going to stay at 2000, that's fine. But the other ones can change. I don't know if that would fix that issue or not. It might. This should still be able to run. 10 is 10. Prtmemmap, that should be updated. Okay, so if we go to editor, let's load. See, we get some garbage there. That's okay. That's to be expected. Control R. That still does that, which is interesting, but I'll look into that in a bit. But it seems to be working mostly okay. So I can go ahead and free the memory now. After they return, okay, we'll free the memory. Similarly to this stuff, I'm going to print out where memory is freed. Except I will call it free. It'll be freeing instead of allocating. And then instead of setting it equal, we just need a call to free blocks. Just go down here. Okay, free blocks, which you probably can't see because of my face, so let me... Okay, free blocks here just takes in an address and the number of blocks to free. It frees them at that address, just unsets the blocks and reduces the used block count by that number. So when we call free blocks, if we allocated 1 block, it'll be freeing 1 block. It needs to be at the address though. Yeah, address and then num blocks. So this will be at allocated address, previously allocated blocks, Right now, this is still single tasking OS, right? So we're only going to have one address at a time, one set of blocks at a time. This isn't super useful, but it does set things up for later. Okay, and then after it's freed, I'll put freed at address, whatever the address was. So that'll be all right. Then we'll continue back. So I will do something similar. Just copy this whole thing. After we read the text file, when we're done, we'll free the memory. Yeah, so that should be good for freeing memory. That's all we really need to do. After we use the blocks, we allocate them, put it at an address, do whatever with the memory at that address. When we're done, we free the memory at that address, the blocks that we allocated. So how many blocks, or yeah, how much data does this take up? The same amount? Okay. Let's call file table. It should say allocating, allocated, runs the data, it frees it, freed at that address. So these should match, and these should match. And then the values in prtmemmap before and after should match, and they do. So that's good. The calculator should be the same way, should just be one block. It's going to be 16. And then after we return, it prints it free to block at that address. We can still load that, so that's good. Sometimes these get corrupted, so I know I have memory issues. That's why I keep calling these every time. And then this is how it was to begin with. So editor is still going to be a bit jank. What if we make a new file instead? It's jank. Probably because it's loading. It's calling load file from the editor. I think that's the issue. Because that's still hard-coded in there to 20,000. But if editor's loaded at 20,000, then it would be kind of calling itself, which would not work, and it kind of triple faults and resets. That would probably be why we're doing that. So I do need to change the editor code and some other things. I might change the spacing as well. I think I could do one less new line here. But that works for allocating and like running stuff at a basic level. And it's pretty simple. I think it makes sense. Freeing blocks at that. I'm going to make this one new line. This is going to be one new line. I wanted this down here from the text file. This is inconsequential, but just wanted it to read a little bit better. That's a little bit better. I'm fine with that. Okay. So I freed it all. We did all that. It's still in hex. Might change that to decimal. I do need to fix the editor issues, so I want to go ahead and do that. All right, let's continue this. I did find the issue where the blocks loaded were going to hex 20,000 every time. I found the issue in there. That was in the memory manager header file. It was a one line, kind of a one character change here. But it was in find first free blocks. Hey, so down here where I was checking if the bit was not set in the memory map, I had if not memory map I and J. So J is the first bit that isn't set, but we were checking one shifted left by J here. So doing memory mapping J was not correct. We need to actually, this is the bit we were checking. This is the bit itself within this 32-bit area that was unset. We need to check that bit. We don't need to check J. J would be the value from 0 to 31. But if we shift 1 by that value, we get the bit within this chunk of the memory map. That is what we need to correctly test against. Testing against just a singular value, 1 to 31, would be something completely different. It would be the whole, 32-bit value, 1 to 31, like a constant. We don't want that. We want the bit value there. So that was a small change there. That kind of fixed that. So that stuff is loaded correctly at A000, like I thought it would be, and like it should be. File table, it's loaded at A000, loads it, freed the block at A000. So, and that also fixed the editor issue from like resetting the OS. So if I load, I know the strings are messed up, but if I load something like the file table, I can return back to the kernel now. It doesn't reset. It doesn't reboot. So the editor takes up 3 blocks, so it frees those 3 blocks at A000 now. Now that works. So if we make like a new file, this should still work. Test text 1, freeze the 3 blocks, it's there. We can load that. We can test the memory map. It's all good. So I can now move on. That is fixed. Now that is fixed. So there's some small issues in the editor. I guess I'll try and fix those right quick. A larger overall issue would be that we are calling load file within the editor to actually load files right now just at 20,000 hex. I do want to change this, but I want the only memory management sort of stuff happening within the kernel. So for a called program like the editor to load something to memory, we already gave the editor like a chunk of memory to work with, right? When we loaded the 3 blocks to an address, the editor's loaded to that address for that given amount of space. So the editor should not have free reign over our address space anymore. That should be the kernel's domain, the kernel's responsibility for memory management. I don't need to cast this either. That's going to be casted implicitly when this function is called. But in order to, allow the editor, allow sort of user space, even though I don't have a distinction, let's say we're allowing user space programs to allocate in free memory. I think in C, traditionally they had malloc and free, or clear and allocate, or reallocate, whatever. We have these memory management functions that'll go ahead and allocate space or free space. So I'm going to try to implement that. That won't be in this video. That'll be maybe in the next one. That would involve probably syscalls, implementing interrupts so that we can have a software interrupt within like a C program here, like the editor. I wouldn't call it directly within the C program. I'd probably call like malloc, however much space we need. Let's say it's 1 block for like a file by default. And internally in malloc, which I'd have in like some other header file, this would call like probably inline assembly functions to implement the system call. And then I'd have some area in the kernel where code and logic is for implementing the system calls. It'll be like an array of function pointers maybe. And we'll say the syscall number will be like 80. Malloc will call 80 in hex, which would be 128. So I'll have like a range of function calls. 128 will go to this syscall handler, and then that syscall handler will look at whatever function we want to do. So if I do like inline assembly within the malloc call, we'll say EAX will be set to like 10 or something. So in my syscall handler, I'll have 128, and then within that there will be like a function 10 will be for like allocating memory blocks or something. And then I'll call our allocate block functions, or our free block functions that we have within that memory manager header file. Since that's included in the kernel, we can probably call that code from the kernel, as long as we set up interrupts to correctly handle all this and jump to kernel code as interrupt service routines. For software interrupts, this isn't to do with hardware yet, but I know I'm like way off on a tangent. That's just load file is going to change here. Because we don't really, I don't want this like just allocating a hard-coded address right now. We don't have virtual memory set up or anything to where that should work, so I don't want it to work. But I will change that. That'll be coming up in the future. I'll be implementing probably some basic system calls and, int 80h, or at least for malloc and free. So free would call something similar to this, except instead of function 10, maybe it'd be like function 11 in EAX, and it would call the free blocks function effectively within the memory manager that we did. But that'll be coming up in the future. Right now, I am going to just leave load and save file and everything alone, so it'll still work for now, unless we end up loading a bunch of stuff and it writes over this memory address. Then this would not be guaranteed to work, but let's assume it's good for now. The issue right now currently in the editor is that some of these strings are like disappearing, or they're being garbled, there's being garbage. And I think that's due to changing the linker file. I took out where the text section in the editor is loaded at 10,000. It's not loaded there anymore. I did run into the same issue in my test environment, that OS, and I fixed it by putting a static in front of these, and maybe a constant as well. I don't remember. I'll try it with static first, but I'll put it right here with these two. Well, I'll just put it in front of all these. But it was just with like these string sort of constants here. They were like not being loaded correctly. They're not being put in the right sections in the final binary or something. I'm not sure. Well, it doesn't have sections because it's not an ELF, but you know what I mean. But if I put static in front of these, you'll see probably, hopefully, when I load the editor, that stuff like enter file name, when we go to load a file, this was garbage, or it was just gone before. It should show up now correctly. I don't know what Clang does, or GCC, if it works the same way. I don't know what it does with the static keyword as far as moving it between data or RO data or BSS sections. If that's what the cause of this is, I'm not sure. But if we load the editor now, we load a file, we have this string show up. file to load. Before this was garbage, but if I add the static keyword, then it works. So I don't know what the compiler's doing with that. I am running these on, I think, -01 for optimization. Maybe that has something to do with it. It moves the strings around in memory, but it does work. We just have to put static in front of stuff. So I don't really know. And if we load and we make a new file and we go to save it, now we have the enter file name text. That was kind of gone before, or it might have been garbage. So, you know, we'll just do that as an example. Test file 1 was not found because I put 2 zeros, but that is found. We can allocate, we're good. All this stuff seems to be working if I type it in correctly, which is never guaranteed, but okay. Put in static keywords for files or programs, for programs that are loaded from the kernel, like the editor and the calculator. At this point, if you have any constant strings, like syntax error, this may not work. We can see. You might want to make those static just to ensure that they work. I'm not sure if that syntax error will work or not. So let's see. Multiply, divide, 1. Okay, so it doesn't print syntax error, it prints a blank. That's what I was trying to show. So let's put like static in front of that, and we'll see if that makes it work. Maybe, maybe not. 10. So there we go, it prints syntax error. So we have to put static in front of that. Not too big of a deal, but kind of annoying. So the only other small thing I wanted to change, or that I did change before, was making some things constant for some very slight optimizations. I'm going to do that within the print string, so maybe also print character, but as far as this print string, this shouldn't affect anything else if I do this, but I'm just going to make this a constant. The string coming into the program, I'm going to make it constant. So in string, that way I don't have to do that. I don't have to set it up for a variable first. And I can check the values on here. The reason I'm not calling it string is so that I can check wherever it's changed here. Just to ensure I got everywhere. So just replace all those with, you know, the end string, the input parm, and then it's a constant now. So that string should be mutable because we're not changing it here immutable because we're not going to change it in this program. But I'll just run everything again just to make sure that, hey, that actually worked and didn't mess anything up. Strings should still be printed, and they are. Okay. So I can make a couple changes here to the editor, the stuff at the bottom, these two things down here, fill out bottom editor message and right bottom screen message. These I can change to constants and other areas too. I just didn't think of them yet. But these can be constant. We're just passing them through because print string is using a constant string right now. I don't need I right here. I don't know why that's there. Get rid of that. And I guess these strings up here, these aren't going to be changed. These can be constant as well, because they're not going to change. So other stuff I could change as well. These are just examples. Oh, but these ones I am not sending constant strings. Maybe I don't want to do that, because that is a lot more errors than I thought would be there. Say file error message. Oh, because I didn't make other things. Yeah, whatever I call to these needs to be constant. Also, probably the function prototypes here. These need to be constant. Yes, that might get rid of a couple errors, probably not, maybe. I guess they'll be casted or they'll have attributes applied or something. I don't know, I should learn more how the compilation process works, so I can not like just spout bullcrap and act like I know what I'm doing. I have no idea what I'm doing, alright. Okay, but everything seems to be okay, so it's working so far. You know, fingers crossed, right? It's working, alright. Okay. I think I said that was the last thing I was gonna do, but I have one more thing. Jackie, you know. His uncle always had one more thing, so I'm gonna make a print decimal function just to make some things look a little better, a little easier to read. Like in the calculator, we get hex results. I kind of want it to be integer results. That's what I'm used to, although I can have like a change the hex mode later. And stuff like the blocks we have remaining, and maybe stuff like directory entries and other things we can make integer. But even if I don't use it, I just want it for the experience, I'll have a print integer function. So instead of print hex, instead of print int, because hex is printing integers, we'll make print dec for decimal, so base 10. We'll print base 10 numbers instead of base 16, right? So I'll do that, .h. Okay, so we'll do the print dec, print decimal integer function here. It's not that big, it's not that long, but it'll just, yeah, it'll print a base 10 integer as a string of characters. So maybe it'd be similar to an I2A or an I2 string function, depending on whatever, you know, libc you're working with. Maybe it has one of those. It'll just be void like the print hex. It'll take in, again, the cursor x and y values as pointers. And right now they're still 16-bit, which causes more code actually on 32-bit. It needs like a size prefix or something, so it would actually be less code overall if I changed all cursor references to be 32-bit, I think. I might do that in the future. Just a small optimization thing there. And we'll have the number to print, so I'll just call it number. But similarly to the hex string, I'll have a string that we're going to print to the screen. I'll call it the int string or dec string instead of hex string. It doesn't need to be 80, but again, I'm just going to make it 80 just for, I don't know, argument's sake. It's easy for me to think, hey, we're still working with 80 character screen kind of in text mode, so we're not using text mode, but that's how I still think of it. But I'll have I equals 0, I'll have j in temp. And for this one, I am going to pass in a signed value. So I will not be able to print the full 32-bit, you know, unsigned range, but I will print in a signed value, so we can do negative numbers, right, using this. So I'm going to have a flag for negative numbers. Eventually I need to make a Boolean as well, but this isn't defined yet. I don't have a type def. So right now I'll just make a 0 or 1 flag, which will be a UN8. And I'll call it negative. So it'll start as 0, meaning not a negative number. So if they passed in a 0, like the print hex function we did, I want to just print a 0 to the screen if they passed in a 0. Simple enough. I will pass in, or well, I will set with index string I++, I'm going to set equal to a 0. So if passed in 0, print a 0. And I'm doing this similarly to print hex. I keep saying that, but they're pretty similar here. I'm using I, which starts at 0. I'm setting it to 0 and moving on, because I'm going to null terminate the string, and like the other print hex function, the number is going to be stored within this character array sort of backwards. So I'll have to swap it around and print it out right to front, or I'll have to print the string out, you know, in reverse so that it reads correctly on the screen. If we passed in a number 123, the numbers would be stored how I'm going to do it as 321 from the beginning of, you know, this string in memory. So if we printed it out as normal, it would say 321. So we'll have to reverse it later, so it says 123. But okay, if we did this, let's do else. Else if the number is less than 0, then it's negative, so I'm going to set the negative flag. So negative will equal 1. But in order to print the number right and to have things work a little better, I'm going to make the number positive. I'll do a sort of absolute value test on this. So the number will equal negative number. We'll make it positive just to make it easier to work with, but we'll say it's negative so we can print a negative sign in front of the number, you know, when we print it to screen. Okay, so similarly, again, to print hex, while number is greater than 0, we're going to get each sort of tens place digit instead of in hexadecimal, it'd be sort of the 16s kind of place digit here. We're working with base 10. So, you know, if we send in the number 123, we want to store off the 3, divide that off, cut off the last digit however you want, store the 2 and then the 1. So we'll store it, you know, within the string here. We'll set dec string wherever I is, that's our position within the string. Wherever that is, we're going to get whatever the number is, modulo 10, so the remainder divisible by 10. If we pass in 123, divided by 10 would be 12, remainder 3, effectively. So the remainder, after dividing by 10, for passing in 123, dividing by 10, it'd be 3. So this will get the 3. And then to store that as a character and not as an integer, as a number, I'm going to add in, you know, the ASCII 0, because that's the start of the numbers in ASCII. So that's, or you could add decimal 48, it would be the same thing. Because the ASCII numbers, 0 to 9, are 48 to, you know, 57. So store next digit as ASCII. And then I want to divide by 10 the number just to chop off that digit. So remove last digit, and then we'll go again. We'll do I++ to move to the next position in the string, store the next digit as an ASCII, and then we'll do that. So after we're done with that and we stored the whole number, all its digits in the string, I'm going to check if it's negative. If it is negative, we want to print the negative sign on the front. So I'm just going to set in dex string I++, I'll set to just the dash here, the hyphen. So add negative sign to front. Okay, and then I'm going to, I keep doing that, and then I'm going to, since we did I++, it's going to be iterated already, I'll set it off with the null. I'll cap it off with the null byte. Because it's a C string, we'll null terminate it. But similarly to the print hex, the number is going to be stored backwards. So I'm going to reverse the string by swapping each end until they meet in the middle. I'll start off with I-, skip the null byte, then we'll do, that's why we add j as another sort of index into our string here. For j equals 0, j less than I, j++, and I-. So each end of the string, front and back, we're going to swap them and then squeeze them in, swap them, squeeze them in by 1. You know, same thing we did before. So again, I'll set temp equal to dex string j. Dex string j will equal string I, so the front will equal the back. And then I will equal temp. That's simple enough. Then the string is stored in reverse, and then we can actually print it out. Print out results. So I'll do print string. Actually, what I could do is also store the string up here. Since I'm calling stuff in there, I probably should do like includes, right? For print string. I know I'm not doing that, but I probably should look into doing that later. Just to ensure that it works. And I don't need to include the other files if they're already there. And whatever this is going to be included in. But I don't know. Regardless, we can just print it out here. Print out the dex string result. That'll work for positive or negative numbers. So what I'm going to do is just right quick put that in the calculator. I'll put it after print hex. Print dec. And whenever we get a result from the calculator, I think it's in, yeah, parse buffer here. If we did not get an error, we'll do print decimal instead, and it should print as an integer, decimal integer to the screen. Here in the calculator, the only issue with this is that since we can print negative numbers, right now I have the error set as -1. So if we get a result that's -1, it's going to print syntax error. So I do need to change that, so I'll probably put a to-do here. Change how errors are handled, and I don't know, what's a good fancy word? Percolated up? Percolated. Back up through function calls. So I'll need a different way of handling that. Let me put an explanation. Because getting a -1 result will print syntax error regardless. That's a bug. Okay, but I'll just make it and show that print decimal actually does work. I think that might have increased the size though. 1A, 1E, 0E. Yeah, from 0D to 0E. So that's fine. 0D, H. So that goes up by 1, this goes up by 1. Okay. At least I don't have to change the boot sector for that, which is good. Alright, so let's get this over there. So calculator, it'll load one block to A00. So if we print in 10, before it was 0xa, right? Because it was hexadecimal, now it prints 10. So 100 minus 20 should print 80. We do 50 minus 100, we should get -50. So the negative sign does work. If we get a negative result though, 2 minus 3, it'll print syntax error because that's -1. So that does need to be fixed, but you know, we can do complex statements now. So 4 times 8 should be 32. Okay. We can do things now, that's good. So is there anything I want to, maybe the freeing blocks and the allocating blocks? that could be print decimal to make a little more sense. Possibly the print memory map, these things could be put into integer blocks or decimal blocks to read better. So, you know, just different areas like that, maybe we could put in print decimal for the future just to be able to read a little bit easier. I'll go ahead and add this to the kernel. And I'll look at some of these print hex here, like the needed blocks. Let's do that. Let's do print dec. When we're allocating, let's just go ahead and do that right now. And then when we free blocks, allocating and free blocks, I think will read a little bit better as decimal integers. And then when we print out, let's say when we print out the blocks, memory addresses, I'm okay with being in hexadecimal because I think that's more traditional for that. But as far as like these numbers here, total amount of blocks we have, I guess that reads well as hex as well. But I'll test this out. We'll make all these decimal instead of hexadecimal. Let's see, that is now 1B instead of 1A, so that'll have to change again. That's okay. The more I do this, the more I get angry at it, which means the more I'm likely to change it to be better, right? Rage-driven development. That's how good stuff is made, you know. Once you get tired of some crap, you make the crap better. But okay, we'll just do that, increase the size there. File table in the boot sector. So when we run it now, we get decimal values. Hey, look at that. Total 4K blocks. 1048, 575, 101, 5976, 32599, 1048, 575. That was the 5 Fs that was there before. Why am I clicking instead of typing it on the keyboard? I don't know, because I'm lazy. I think that's the number it was before. 32599, 7F57. So those are all correct, so that's good. So if we load something, we allocate the block. Allocated to address, well, I probably don't want that address to be there. That address should be different. But that is correct. 4096 is 1000 in hex. 1000 in hex times 10 is going to be A000, 10,000. So, and since each block is 4096, we multiply by 10, so it puts a 0 on the end. That's the right address, but yeah, I'll change that back to be hex, because that just reads weird. But allocated and free in blocks, that is correct. So that looks okay. Let me change that right quick. I changed a little too many things and did not read what I was doing. This address, the address is, I do want to be hex. That address down there. This address down here. Okay, allocated address here. We only allocate it once, but we free it twice. Okay. In two different places, rather. Don't want to free it twice. That'd be double free. That's a different kind of error. But all right. Okay, there we go. Allocated to this address. That looks a bit better. Load this up. Return 3 blocks at that address. That looks pretty good. So, okay, I think we're in a decent place now. We got a sort of basic memory manager working, physical memory manager. Although, again, this is only for one thing at a time that's being loaded and ran or just read to the screen as text. So, you know, single tasking, I keep bringing that up because eventually I do want to move into multiple processes at once in some way, I guess, if only to learn how it's done. Yeah, the stuff I'm thinking about for the next one is either making maybe like a little menu or a window or having the user enter in the graphics resolution, the graphics mode that we want to do for VBE. That'll probably have to be done within the bootloader, so assembly code, but if somebody doesn't have or they don't want to run 1080p, or if I want to run this OS on actual hardware, like my old laptop, it doesn't have a 1080p screen, I want to be able to choose a different screen size and maybe bits per pixel value. So I would have to change how printing text is done to make it more generic, to take in some values that I store at some location in memory, like a kernel memory area that I put in graphics values that I get from the bootloader where the user chooses what they want, something like that. Text printing would be made more generic. So the font, maybe I can make that generic as well, or at least add values somewhere to make it abstracted in the future. I don't know. But I'm thinking about that, making graphics user changeable or a little more generic, easier to work with. instead of hard coding stuff. And it might be that, it might be an assembler that I've been working on, starting an assembler and doing code. But I guess if I'm going to be loading and editing within the OS, then I also, what I was saying earlier, I want to make like software interrupts or a system call system. So yeah, putting in an interrupt descriptor table, putting in software interrupts, ISRs, to call at least int80h or whatever number we choose. Linux has int80, so that's 128 in decimal. That would go to a sort of generic system call handler, which would be in the kernel. It would dispatch to, you know, whatever the 128th system call is. Well, that would be set up in the interrupt descriptor table, sorry. It would have each section for ISRs, which would just be basically a pointer to wherever the function is that handles that. So int80 would be 128 in decimal. So the 128th entry in the interrupt descriptor table would go to a function that handles int80, int128, as a software interrupt. And then that function would be in the kernel, okay? And then we would need a way to determine what function within int128 the user was saying. So if they did int80 and set EAX to 1, that would be like, I don't know, open a file or read a file, whatever it is on Linux. So within our int128 handler, we'll call it, within the kernel, we would have like maybe an array of function pointers or something, and we offset into that by the value in EAX. So we get that value with inline assembly. We'd say, okay, the user put in 1 to EAX, we want to allocate memory. So then we call our allocate blocks function for however much memory they wanted. Maybe that's in like EBX or something. And then we allocate that many blocks, and then the kernel can keep track of that. And then whenever the program is returned to, whenever that program ends, and then we need to, you know, keep track of and free that extra memory that was allocated at runtime to that user program, that user process. This is all up in the air and abstract. I think I'm saying that right. I'm not sure. I could be talking out of my butt, you know, but that's probably the line of thinking I'm going to go on, and development I'm going to try to do. And I haven't done an IDT yet, so I think interrupts would be cool. At least software interrupts, a little easier than hardware interrupts. We don't have to program an interrupt timer controller yet, so I might go with that because that seems interesting. So maybe look forward to either interrupt descriptor table, int80, we'll say allocating and freeing memory functions, malloc and free, some basic form of that, for the editor to call to load files to. Maybe I'll do that in the next one. If not, then maybe making the user graphics changeable, the graphics mode. Maybe these colors I can make changeable as well. That would be good. So maybe one of those two things for the next episode, but I'm rambling way too much. So all in all, I appreciate it. Keep getting subscribers and people watching for some reason. I figure my videos are boring, but people like them. So at least to some extent. And for that, I'm very grateful. So thank you all. I do appreciate it. You're all wonderful people. Hope you have a good time wherever you're at, or I hope things get better if they're not, but I do appreciate it. Thank you for watching. I will see you on the next one.